So I would like to welcome all the participants on the 2022 edition of the Integrability in Gauge and String Theory Conference here in Budapest. We are very proud that we can organize this, this nice meeting, which has a long history, which goes back to 2005. I think it was 2005 when in Paris, the first conference was held, and the two founding fathers of this conference, Matthias Staudacher, who I can't see here, and Volodya, who will come tonight, who initiated this whole conference. I would like to thank many of you. First, probably the advisory board, including these two founding fathers, and also Gigina Serban, and Charlotte Christiansen, and Roberto Tateo, Kolya Gromov, and Pedro Vieira, who unfortunately couldn't come because his flight was canceled. So I would like to thank also for this advisory board for suggesting a very nice list of possible speakers, out of which the local organizers has chosen this list. And I thank the speakers themselves for accepting the invitation and for preparing for their talk. And then welcome Matthias, the founding father of this conference. I would like to also thank the sponsors for the financial support. First of all, the National Research, Development and Innovation Office of Hungary, then the Mecenatura Grant, the Wigner Research Center for Physics, and also Gotis Plus, who supported some accommodation and travel expenses of the young researchers, and also will support a prize for the best poster and also a prize for the best young speakers. So we have two committees who will decide actually about these two prizes. So the conference, you can see the program of the conference. I will say first a few words about the technical implementation. So we would like to be as green as possible. So in the coffee breaks, we provide a cup to everybody. So this is plastic-free July. So please use this cap, nurse it, pet it, wash it, and reuse it. You can drink coffee. You will see you can drink wine on the poster session, which is going to be today after the last talk at 6 o'clock, where we will have some nice wine and pogača. You will learn what is pogača. Yeah, maybe also one other thing I should mention, that the new COVID cases are rising in Hungary now, not very steeply, but still rising. So we advise to wear a mask when you are not speaking. It's not compulsory in Hungary, but nevertheless, it's a good precaution. And that's the reason actually we moved into a bigger room. This was not originally what we planned. So we will have this kind of minimalistic coffee break. If you don't feel safe here, then you can bring your coffee outside and you can drink it there. We will have lunches, free lunches for all of you, for all the registered participants. This is a very nice place. It's an all-you-can-eat place. All you can eat like 120 dishes, and then a nice wine, beer. The price you have to pay, sort of, that you have to walk there, and it's 20 minutes walk. And we try to leave around noon in front of the building together. So this is going to be on Monday, Tuesday, and Thursday. On Wednesday, around noon, we will have a photo session. We will take the conference photo, and at the evening, we will have a conference dinner, which is in the usual history of this IGST conferences. It's going to be a boat trip on the Danube. So if you would like to join, then please register at the secretary. We would like to know. Also, if you don't want to come for the lunch, please tell the secretary, because we have to come. So the conference will end on Friday at noon. And the Hungarian Grand Prix is just following, so if you are interested in, you can stay. If not, then we will have just a closing speech and finish the conference. So that's about the week. And I would like to wish you a very nice meeting. Enjoy the conference. And I'm asking Bogdan Stefanski, the first chairman, to chair the first session.
Hi, I guess let us start. While Marcos gets ready, I'll tell you he's going to talk about resurgence and renormalons and integrable quantum field theories.
Okay, thank you very much for the invitation. It's really a pleasure to be here in Budapest. I have been already here for a few days, and it's a fantastic city. I'm very happy to have been invited to this conference. So I'm going to talk about resurgence and renormalons in integrable quantum field theories, and this is mostly based on work with my postdoc Ramon Miravillas and my student Thomas Reis. Okay, so I see that the equations are not shown in the computer. Which is something that has happened before to me. So I don't know if there is any way to fix this or no. There is an equation missing there, yeah. Yeah, there is, yeah, some of them show up, but you see here it's already like quite. So it's, yeah. So is there any way to, this happens sometimes with the PDF files generated by Keynote, but I don't know how to solve this actually. Yeah. This is a PDF file. So this is the PDF file, so I don't know.
You already turned it?
Yes, yes. So you say, this is this.
Próbáljuk ki, erre rá tudjuk.
I don't know, you can. No, but you know, it works most of the time, but it's just, it's not the first time it happens to me. Yeah.
Do you have HDMI?
No, I don't have it yet.
I don't think so. Van bármilyen átalakító.
So I don't know. What
if you switch the talk and then you talk after the coffee break?
Okay, fine. Yeah, yeah. Okay.
So Florian, sorry, it seems we have some problem with displaying the equations. So I think it would be a good idea to switch to first two talks. So if Florian is here, please, could you come? Yeah. Yeah. Do you have also equations? Do you have also equations in your slides?
So Marcus, thank you for that inspiring talk. Our next speaker is going to be Florian Lobert, who is going to talk about Youngian symmetry, fishnet integrals, and geometry.
Yeah, okay. Yeah, first of all, thanks a lot to the organizers for the invitation to talk here. So this is actually about a research direction that we've been pursuing for a number of years now. So it touches several papers of the last years with these collaborators here, and in the second part I will tell you about the most recent developments together with this group of people here from Bonn. So I guess we are all here because we work on integrability, because we share this opinion of Hermann Weyl, who says that whenever he had to choose between the true and the beautiful, he chose the beautiful, and integrable structures are certainly a very beautiful subject. And I think from the particle physics perspective, the IGST correspondence has clearly helped to reduce the gap between truth and beauty, because it brought integrability to four-dimensional quantum field theory. Still, n equals 4 superhang Mills theory is probably more beautiful than true. So it would be nice to close this gap a bit further and to see whether integrability can help more in the direction of particle phenomenology. And where could integrability actually help? There's one big bottleneck in the computation of scattering amplitudes, cross-sections at particle colliders, and that's still the computation of perturbative Feynman integrals at higher loop orders. If you are at low loops or lags, this situation is under quite good control by now due to the work of a number of people. And there you have integrals arising that have this structure with a rational integrand that you can iteratively define to find these multiple polylogarithms whose mathematics is quite well understood by now. But if you go to higher loops, new function classes appear. You have integrals where you have higher order polynomials, roots of higher order polynomials, so you can't reduce them to these multiple polylogarithms anymore. And this is a very active area of research. Currently, people are trying to understand the function classes, the building blocks needed to compute these Feynman integrals and thereby scattering amplitudes and cross-sections. There are really dedicated workshops and conferences by this small industry that works on the computation of Feynman integrals. So this talk is about the connection between integrability and Feynman integrals. In the first part, I will just briefly tell you that by integrability, I actually mean Youngian symmetry. Here, I will then tell you how massless Feynman integrals inherit such a Youngian symmetry from the planar IGST correspondence. I will briefly sketch how this generalizes also to massive Feynman integrals, which a priori is somewhat surprising. because in the context of a massive phase of IGST of n equals 4 super Mills theory, we don't know of any integrable structures so far. And finally, I will come to an application to fishnet integrals, which leads to a nice connection to geometry. So, as I said, for the sake of this talk, by integrability I actually mean Yangian symmetry, and just one slide on the Yangian here. So it's an extension of a Lie algebra, and the most important thing for this talk is that it's generated by these two sets of generators here. So at level 0 you have the ordinary Lie algebra generators with a trivial tensor product action that are constructed from some densities. And in this talk, this tensor product will actually be given by the external legs of your Feynman integral. And then you have a set of so-called level 1 generators that are constructed from the same densities here, but you take two of them and sum them over all relative positions on this tensor product. You also have these Serre relations, but they won't play a role for this talk. So the important thing is that you have these two sets of generators that span the Yangian algebra. And there are all kinds of examples of rational integrable models where the Yangian plays the role of the algebraic underpinning for this integrability, the Heisenberg spin chain where the Lie algebra is SU2, or IGST where you have PSU2, 2/4, and the Yangian appearing in all different contexts. And typically, before, Yangian symmetry was investigated in the context of 2D theories, spin chains, 2D field theories, where the consequence is that the scattering matrix in these field theories or spin chains factorizes. So let me now tell you about this connection to Feynman integrals. I'm actually interested in this very special class of Feynman integrals that has played already an important role in the last years in this community. These fishnet Feynman integrals, which are easy to construct. So you have one integration vertex. These are position space Feynman rules and propagators of this form. So they are given by 1 over xjk square, where xjk is just the difference of these space-time coordinates. And the square just means the contraction of Lorentz vectors. So this is an example of these graphs. Every dot here corresponds to every solid bullet corresponds to a loop integration. So in principle, these are very complicated integrals. And the only integral that's really under full control is this most simple example, namely the cross or box integral. So I will equivalently say cross or box, because if you go to dual momentum variables that are related to these axes by this equation here, then the dual graph looks like this, and you really have a box here, which in momentum space is your loop of integration. So despite being very complicated and mostly unsolved, these graphs have very nice properties. They have conformal symmetry realized by such differential operators. So here you see this sum over the external legs, and the momentum generator is just the derivative. They are finite, and which makes it very convenient to work with them. And as I will tell you now, they are related to IGST integrability. So also just one slide on this, which has been discussed a lot, and we will hear more about this, I think, in the following talks, about this connection to the fishnet theory and Feynman integrals. So we start with the Lagrangian of planar n equals 4 super Mills theory here in the upper left corner. Then we introduce what's called the gamma deformation that has been investigated by many people here in the community from different directions. So you take products in the Lagrangian and replace them by non-commutative products, which gives additional factors here that depend on the Cartan charges of the fields. And the important thing is that you introduce 3 new parameters, gamma 1 to 3 here, which gives you then a Lagrangian that depends on the coupling constant and these 3 additional parameters. And then Volodya and Oemer realized that you can take these special double scaling limits. In particular, in the simplest case, you can take a limit where the coupling constant goes to 0 and you take one of these parameters to imaginary infinity, while keeping this product here, coupling times this exponential factor fixed. And this psi, this product, then gives you your new coupling constant. And in this very restrictive limit, most of the fields of n equals 4 supermix theory decouple, and you end up with this very simple biscalar Lagrangian. You have two scalar complex matrix valued fields that are coupled by this single 4-point interaction vertex. Yeah? So to complete this theory, there are subtleties. You have to add double trace terms, but for the sake of what I'm looking at, these won't play a role here for these correlators I'm interested in. So because there's only this particular chiral 4-point vertex, this theory is non-unitary, which from a physicist's perspective is a priori a downside. On the other hand, this has a very nice advantage that if you write down a correlation function like here, so you take a sequence of fields, x, z, x bar, z, and so on, and want to compute the correlator, then there's only a single Feynman integral that you can write down. Because now this 4-point vertex here should actually have arrows on the lines, and that means you can only draw a single graph. So in this theory, these correlators are in one-to-one correspondence with individual Feynman integrals. And that's nice because correlators in n equals 4 typically have nice properties with regard to integrability. So one can expect that also these correlators in the fishnet theory, alias Feynman integrals, inherit some of these nice structures. And in fact, one can show that they are annihilated by these Yangian generators, in particular by these Yangian level 1 generators, which when they act on the kinematics of this Feynman diagram, yield 0. So we see that via this mechanism, we get integrable structures for Feynman integrals. So this is very abstract. Let me tell you more explicitly what this means. I told you about these two levels of the Yangian. The level 0 is just the conformal algebra that you get by whose action you get by summing over densities, and the densities are just these differential representations of dilatation, Lorentz, momentum, and special conformal generator. And it's well known that conformal symmetry implies that then a Feynman integral, an n-point Feynman integral, is given by some prefactor that carries the conformal weight times the conformal function phi that only depends on these conformal cross ratios. So this is already a big simplification as compared to the general Feynman integral. Then you have these additional level 1 symmetries. I already gave you the recipe how to construct them. So you take the same densities as written up here. For example, the level 1 momentum generator looks like this. You have the Lorentz density, dilatation, and momentum density, and you sum over these ordered positions. And this means that this is, again, a differential operator, but now a second-order differential operator that acts non-locally on the external legs of the Feynman graph. So now Yangian invariance means this equation here, the level 1 momentum, annihilates the integral. And for these fishnet graphs, we can write this in this particular form. We pull out some space-time vector, and here we get a differential operator that I denote by PDE, which is a differential operator only in these conformal cross ratios. And one can argue under certain conditions that these vectors here are actually independent, so that we can read off a set of differential equations from this Yangian invariance condition. And this is the main message here. Yangian symmetry translates into systems of coupled differential equations in the conformal variables. So here our favorite example, the simplest integral, the box integral. Again, here are these two equivalent representations in X or P space. The conformal symmetry implies that the integral can be written with this overall weight-carrying factor and a function that depends only on the conformal variables z and z bar, which are defined through these standard conformal cross ratios here. Then the Yangian symmetry implies that there are two differential equations that this function has to obey. So here J can take values 1 and 2, and these are the explicit differential operators. These are second-order differential equations, and you can solve them by elementary methods to find 4 solutions. So the solution space is spanned by these 4 functions here. And now you can use in addition that this integral is actually invariant under any permutations of the external points. So if you exchange 2 of the external points, the integral will be the same, so permutations are symmetries of the integral. And these permutation symmetries single out this last function as the only possible solution compatible with Yangian symmetry and permutation symmetry. So this is actually the well-known Bloch-Wigner dilogarithm, which has been known to correspond to this integral for some time already. But here we've shown that we can actually fix it just using the symmetries, this Yangian symmetry. So you may wonder why there are actually 4 solutions, whether Yangian symmetry does not pin down the whole thing completely. And in fact, one needs these other 3 solutions to express the integral in Minkowski space. And as we've shown with Matthias and Luke and Julian. So the Yangian actually spits out all the building blocks that you need to completely write down this integral. So this, in Minkowski space, you will have to take different linear combinations of these functions depending on different kinematic regions. These are all the Yangian invariant building blocks that you need to express the integral. So far, we only discussed massless Feynman integrals, and in particular with regard to maybe possible phenomenological applications. Of course, masses are also very interesting to consider. So let's think about generalizing this to the massive case. And you remember that in the massless situation, the logic was that we start with planar n equals 4, we take this fishnet limit where correlators are individual Feynman integrals, and then we argue that these Feynman integrals should actually inherit integrability properties. Of course, people have looked at massive phases of n equals 4 by giving a VEF to one of the scalar fields, so introducing mass via the Higgs mechanism, which leads to propagators of this form here. So before we had these massless difference propagators, and now we have masses also appearing as differences here. And there's also a well-known generalization of conformal symmetry to this massive situation, which takes this form here. So now we also have derivatives acting on the masses, which actually take the role of an extra dimension of a 5th or d+1th dimension of your space-time vectors. But unfortunately, there's no integrability, no Yangian symmetry known in this massive phase of n equals 4 super Mills theory, so we cannot just follow the same logic here, start with an integrable massive n equals 4 and deduce such implications for Feynman integrals. So what we did instead was to look at massive Feynman integrals directly, just to look at examples. So this is a 2-loop example where now the solid lines denote massive propagators, and this dashed line here is a massless propagator corresponding to the hatted and unhatted axis here. We've seen there is this well-known massive generalization of conformal symmetry, which gives us the level 0 generators, and we have a recipe how to construct from them level 1 generators. So we can simply write down a candidate for a level 1 generator. And when one acts on these Feynman integrals, the situation is actually almost better than expected. So at one loop, actually all graphs have the Yangian symmetry. Here I even introduced generic propagator powers. And as long as these sum up at this vertex to the space-time dimension, so we can make the thing even d-dimensional, we have this Yangian symmetry for any one-loop graph, no matter whether the propagators are massless or massive. At 2 loops, the situation is also quite nice. So we have a large family of graphs. The only restriction is that this internal propagator here has to remain massless to have this massive generalization of Yangian symmetry. So this one can really prove analytically by acting on the Feynman integrals. At higher loops, we have only numerical indications so far, but our conjecture is that actually you can take any graph cut from a regular tiling of the plane, so from a square, hexagonal, or triangular lattice, and as long as the propagators in the bulk, like here, remain massless, you still have this Yangian symmetry. So all the propagators on the boundary can be massive to have this symmetry. So since there was this nice connection between massless Feynman integrals and this massless fishnet theory, we also thought a bit about generalizing this. And with some more technical input, one can also take a certain limit theory of n equals 4 on the Coulomb branch, which leads to such a simple generalization of the fishnet theory, which is given here in the first line. So we just have these massive terms here, and the important thing is that the masses enter in these differences, just as in the Feynman integrals we've seen before. So this is not exactly the same as if you do spontaneous symmetry breaking in the fishnet theory. So it gives a slightly different theory, which is particularly reflected in these coefficients here. And the interesting thing about this theory here is that also here one can argue that off-shell scattering amplitudes, which map to these dual graphs, to these X space graphs, are exactly in one-to-one correspondence with these massive Feynman integrals for which we found this Yangian symmetry. So it seems there are integrable structures present in this massive quantum field theory, and I'm not aware of any other context where quantum integrability appears in four-dimensional massive quantum field theory. So I think this is an interesting direction, and it might hint at further integrable structures to be discovered on the Coulomb branch of n equals 4 super-Young mills. So also this massive Yangian symmetry we can study. We can look what are the consequences. So let's look at this nice family of one-loop graphs, because we saw that all of them have the Yangian symmetry. They are particularly interesting because a couple of weeks ago this paper appeared here, which argued that in fact contact Witten diagrams are exactly the same as these integrals. So one can write them in a particular representation so that one can identify them, which implies that these Witten diagrams have the same Yangian symmetry. So there is also at least there are some traces of Yangian symmetry in this holographic correlator story. And it's exactly this class of Feynman integrals. So if we evaluate our Yangian constraints, again, this massive generalization of the conformal symmetry implies a dependence on some cross ratios. And here the massive generalization of the cross ratios looks like this. This is really these are the good variables in this massive case. And again, Yangian symmetry implies partial differential equations for these functions phi here. And we can go through the different cases, through the different numbers of external points. For 2 points, we just have this bubble type integral, and we can solve the Yangian equations directly to find the Gauss hypergeometric function with some overall prefactor here. At 3 points, one finds by the symmetry arguments the so-called Srivastava hypergeometric function HC. And then if one looks at higher points, one can quickly see the pattern and write down a generic formula for such a hypergeometric series that corresponds to these integrals. And in fact, this conjecture was also verified by these people here, who actually in this context developed a higher dimensional Mellin-Barnes approach, so they can algorithmically solve the corresponding Mellin-Barnes integrals and really confirm that this is the right hypergeometric expression. So one thing I haven't told you so far about these integrals is that they have nice geometric interpretations. Yeah, these massive one-loop integrals that I've shown you actually relate to simplices whose angles are given by these kinematic combinations. So they compute volumes of these polytopes or simplices. And in particular, in the massless limit, the most prominent example is this cross or box integral, which we've shown is computed by the Bloch-Wigner dilogarithm. and this actually corresponds to the volume of an ideal tetrahedron. This is a classic result that's well known. But I think so far all the examples where Feynman integrals compute volumes are limited to one loop integrals. And a natural question might be whether such a thing actually generalizes also to higher loop integrals. And if we want to get higher loop integrals under control, of course, this is in general a very complicated problem. I told you only this cross integral of this family of fishnet integrals is really under good control so far. So a good idea might be to reduce complexity, and here we do this by going to 1 or 2 dimensions. Yeah? So we look at these fishnet integrals with propagators that look like this, and where we choose now the propagator powers that they obey the conformal condition in 1 or 2D. So they sum up to the space-time dimension, and that means the propagator should be 1/4 or 1/2. An interesting fact is that these integrals now correspond to correlation functions in this d-dimensional generalization of the fishnet theory, which was introduced by Volodya and Enrico. So they also have a, in some sense, physical interpretation, these individual Feynman integrals. The simplest example is now again the box integral, and now we are in 1D, so I think this is really probably the simplest one can get. And this integral one can really compute directly in Mathematica. Yeah? And one finds this combination of 2 complete elliptic K integrals whose definition is written down here. Yeah? So as I said, this is really simple. You can get it in Mathematica, but still, let's look at it from this Yangian perspective. Again, we can write on the Yangian generators, which in this 1D case is just given by the algebra SL2R. And the level 0 symmetry just means that the integral depends on this function phi of a single cross-ratio variable. Then the Yangian differential equation, it's actually a single differential equation in this case, happens to be the Legendre equation, which looks like this, and this has exactly 2 solutions, namely this power series, this K of Z, and this what I call single log solution K of 1 minus Z. And I write this down here in this slightly peculiar way, writing it as a power series in the log times a power series, because this is actually the structure that will generalize also at higher loops. So Yangian symmetry tells us that the integral is given by this solution vector K of Z, K of 1 minus Z. So we know that we can write it as a constant vector contracted with this solution vector. And you could use some numeric data points to indeed find that this constant prefactor is just given by what we've seen on the previous slide. If you go to 2 loops, you have 3 variables here, so a function of 3 variables. Again, you can use the Yangian to generate differential equations. So here's an example. It's a second-order differential equation in these 3 variables. And you get some differential equations from this, but one important point is that you get actually less than in higher dimensions, because you don't have these space-time vectors x mu, of which you could argue in higher dimensions that they are independent, so you get less differential equations from this Yangian symmetry. But there's actually a nice trick one can apply here. So I told you already that permutation symmetries of the integral play an important role. We used them already in the context of the box. And now we use these permutation symmetries, so I can exchange any of the legs sitting at the same integration vertex, and that's a symmetry of the integral. And I can directly apply them to the Yangian generator. Yeah? So any permutation sigma I can apply to the Yangian generator, which is not invariant under the permutation. So this will give additional differential equations so that I get a larger set of differential equations from the Yangian and the Yangian combined with these permutations. And then one can apply what's called the Frobenius method for Fuchsian type differential equations. And also at 2 loops one finds a similar structure here. One finds 1 power series solution, 3 log times the power series solution and 1 double log solution. Since we have more variables, the structure becomes slightly more complicated, but it's in principle the same pattern. So we have a 5-dimensional solution vector, and indeed we can fix a constant prefactor here, prevector, to express this conformal function for this integral. This actually generalizes to higher loops, to the so-called family of train track integrals, whose name comes from this dual green graph here, which looks like a train track. And you see exactly here this solution pattern, one power series, 1 log, 1 power series, 3 log, 1 double log, and so on. And the associated geometry in the one loop case is the elliptic curve, then you have a K3 surface, and in general these are Calabi-Yau L-folds. So at L loops you have a Calabi-Yau L-fold that describes this integral. And this is interesting because there is a work by Matthias and collaborators who investigated train tracks in 4D and argued that these actually corresponded L loops to L-1 folds. So there's a slight shift in this parameter. And even for general fishnets, one can argue that these have this Calabi-Yau structure, so they are related to geometry in this way. And for the connection to integrability, the most interesting thing is that the Yangian plus these permutation symmetries, in the sense that I've described on the previous slide, actually generates the so-called Picard-Fuchs ideal of differential operators whose solutions are the periods of these Calabi-Yau L-folds. So there is a connection here between geometry and integrability. If we go to 2 loops, things become even better. So you can split up the Yangian in holomorphic and anti-holomorphic part and actually reuse the Yangian invariants that we found before. We use the same solution vector pi at the same number of external points in 2 dimensions. And the integral takes this double copy form. Yeah? So we have this solution vector of z times some constant matrix times the complex conjugate variable z. This can also be multiple variables z1 to zn. And indeed, if you look at the simplest example that has first been given by Enrico and Volodya in this form, it's given as a linear combination of 2 factorized Yangian invariants. Yeah? And you can bring it exactly into this form, the solution vector times the matrix and times the Barth solution vector. A natural question is what the role of this matrix sigma is. And here we can remember that these fishnet integrals actually have an interpretation as correlators in this d-dimensional fishnet theory of Volodya and Enrico. And in this context of Calabi-Yaus, there's actually a natural single-valued function. This correlator should be single-valued, and this is the scalar potential. And in fact, we observe exactly that this integral with this structure is given by e to the minus v, where v is the scalar potential of this Calabi-Yau L-fold. And this is nothing but the volume of this Calabi-Yau L-fold. So there is a nice relation between volumes and higher loop integrals. In particular, in this Calabi-Yau context, it's known how to compute this so-called intersection matrix sigma. So we can now say that we can use the Yangian to compute these vectors pi and this Calabi-Yau framework to compute the intersection matrix, and then we have an integrability and geometry-based way to compute this Feynman integral. Let me finally just give a comment on this by now well-known Basso-Dixon formula. So Benjamin and Lance found that if you look at these fishnets in a 4-point coincident limit, then there's a very nice determinant formula for these integrals. And Enrico and Volodya generalized this to 2 dimensions, and this is just very schematic here. There are actually additional factors in the real formula. I just wanted to sketch it. And here you see already a glimpse of this double copy form. So you have a square of this hypergeometric function pfq for these values of p and q. And you can check explicitly that this gives exactly this structure here, where the intersection matrix is somewhat hidden in these epsilon derivatives that you set to 0, this auxiliary parameter that you set to 0 in the end. So there's also a nice connection to this Basso-Dixon formula. Just one more comment on the Yangian symmetry. The Yangian does not commute with this coincidence limit. So the graphs here on the right are not annihilated by the Yangian level 1 generators. They rather, the respective differential operators, rather induce such dimension shift relations. Yeah? So we have an alpha times beta Basso-Dixon graph in d dimension, and these Yangian differential operators map it to a d plus 2 dimensional integral where also some of the propagator powers are shifted. And this is reminiscent of these contiguous relations for hypergeometric functions. For example, 2f1 obeys this relation. The differential equation is mapped to such a shift in the parameters, and it would be very interesting to really solve this equation in a similar way, which might lead to a generalization of Basso-Dixon to graphs with generalized propagator powers. So let me conclude. So we've seen that integrability is present in the context of four-dimensional quantum field theory, also beyond n equals 4 Mills theory, namely in the building blocks of quantum field theory in Feynman integrals. It even extends beyond the massless case, so you can find this Yangian symmetry for integrals with massive propagators. And it relates to the theory of Calabi-Yau manifolds, and I think this has not been seen before, that there's actually Yangian symmetry related to this Calabi-Yau theory. From the geometry point of view, we see that Feynman integrals also at higher loops compute volumes of geometric objects, and I think this is also the first example where they compute volumes of different quantities than polytopes. I think these one-loop examples were always some kind of polytopes. And we even have a geometry and integrability-based way to compute the Feynman integrals via this double copy form here. The Yangian generates this Picard-Fuchs ideal of differential operators, with the Calabi-Yau periods being the solutions. And the interesting thing is that it really seems to give all the differential operators, so the complete set of differential operators and the complete set of basis components that you need to express these Feynman integrals. And I think the general lesson is that these 1 and 2D fishnet models are really instructive setups for studying the involved function classes that are currently under investigation also from the amplitudes of Feynman integral community. Let me just briefly give an outlook. There are really many things to do, many open ends to understand. Maybe the most direct would be to look at these 2D integrals and to introduce the masses there to see what meaning the masses have in this geometric setup. To go back to 4 dimensions and to apply this Yangian approach to 4-dimensional fishnets, now with the new insights on these solution structures. You can also find similar higher symmetries in the context of divergent integrals, so in the context of dimensional regularization, and I think it would be very interesting to further pursue this, because this is the kind of integrals that you typically find when you have a real-world problem, that your integrals are not finite. And another question would be, what volumes or what geometries do actually other fishnet structures correspond to, triangular or hexagonal fishnet integrals? Then, with regard to this question of massive integrability, we've seen this massive fishnet theory, for which so far the only indication for integrability is the Yangian symmetry. It would be nice to find other indications that this theory is actually integrable, and one approach might be that of Tristan, Raoul, and Anne, who looked actually at in the massless case at the spectrum of the dilatation operator in n equals 4 and depending on the distribution of energies can decide whether it's a chaotic or integrable system. And it would be nice to apply this maybe also in this context of the massive fishnet theory. Maybe there's a straightforward massive generalization of this dual fish chain model by Amit and Kolya. Then with regards to pure mathematics, I think this relation between the Youngian and this Picard-Fuchs ideal for the Calabi-Yau periods is a new thing, and there's actually a large community of people investigating Calabi-Yaus with a physical or purely mathematical motivation, and it would be interesting to clarify what the role of integrability here is in a larger context. Probably there are more higher loop integrals that compute volumes of geometric objects. It would be nice to further explore this space. And finally, we've seen this paper on the correlators in ADS, on this relation to Youngian symmetry of Witten diagrams, of contact Witten diagrams. It would be interesting to see whether this is just a coincidence or whether there's more behind this, and whether this also generalizes to other diagrams in this context of holographic correlators. Thank you.
Thank you, Florian, for that very nice talk. Do we have questions? So if you just maybe wait until the microphone arrives.
Hello.
Hi.
So you're so far, I feel almost online.
Sorry, say again?
No, it's not a question. You're so far from here that I feel I'm almost on Zoom now.
I see, okay.
So the question too, actually. First, can you do inhomogeneities as part of the story? For Youngian, can you do inhomogeneities there?
Whether we can deal with inhomogeneities? Well, we have them already in the game. That's, maybe I have a, I haven't given you all the technical details, but we have, the Youngian generators actually have such a tail here with the evaluation parameters. And these depend on the inhomogeneities of your monodromy matrix, and you have to choose the inhomogeneities depending on the graph. So there's a clear pattern, and here are actually the rules. If they translate to these evaluation parameters. If you are at some leg of your graph and you go from one to the next leg, depending on whether there's an internal propagator in between, you either add this combination or this combination, and the A's and B's here are the propagator powers of these propagators here. So they already play a role.
So they're there, but they're fixed, right?
They are fixed. You want to well, no, the A's don't have to be fixed. They can still be parameters. We can deal with integrals which have generic propagator powers. Yeah.
Okay. Yeah, I see. And the other question is, so you say that, okay, these diagrams compute volume of Calabi-Yau, right?
Yeah.
Yeah, so did you think what other cohomologies computed for by?
We haven't, well, this is just a new thing we found, so we haven't looked further at the moment. I think it's not clear which classes of geometries can appear in the context of these Feynman integrals, whether it's only Calabi-Yaus or whether there are worse things appearing.
No question about Calabi-Yau. The manifold volume, it's higher cohomology class, but there are also other cohomologies in this manifold, like lower rank cohomologies.
And you want to do what with them?
Maybe there is an object that computes them.
It's possible, but yeah, at the moment I don't know.
Okay.
Okay, more questions? Yeah, I think Shata has a question.
Yeah, I guess it's related to the second question of Dima, but is there any new things? Is there any new thing that you can kind of like learn or compute about Calabi-Yau using this connection with integrability in Youngian?
I think the statement that this Pika-Fuchs ideal is computed by the Youngin is a new statement. So, I mean, my collaborators, in particular Albrecht Klemmy, is really an expert on Calabi-Yau's, and I think this is something that is not known so far. So it's, yeah, it's really a helpful tool here to generate these differential equations. I think, yeah.
Okay, more questions? Yeah.
Hi, very nice talk, and I wanted to ask about higher points. We know that the elliptic functions that you presented in the beginning can appear also in 4D if we consider higher point integrals, namely 5 point in general kinematics or just 6 points even on the plane. Therefore, can you make some statements about that using Youngian symmetry, because these are very complicated objects to compute, even if we restrict to planar fishnets, right? So, did you explore?
I think the same function classes that you have here in 1 and 2D will appear in 4D as well. So, Matthias and collaborators have looked at these train track integrals in 4D. We can look at the integrand in the Feynman parameterization and argue that this should correspond to Calabi-Yau L or L-1 folds. So the same geometries apply. And we can write down these Youngian differential equations also for higher point Feynman integrals. We've done this for the 6-point two-loop integral. So I should also have this somewhere here. So these are the differential equations for the double box integral in 4 dimensions, yeah? And you can solve them in terms of hypergeometric functions, 9-fold hypergeometric functions, and these people with their Mellin-Barnes approach actually fixed the linear combinations. So you have formal expressions in terms of Youngin invariant hypergeometric functions. And I think now we have gotten really better understanding of the solution structure from this 1 and 2D theories. I think we could now go back to this and look again at these differential equations and maybe better understand how these solutions are related to the geometry. Yes.
Okay, and related to this, since in 4D there is this appearance in Basso-Dixon diagrams of determinant structure, could you somehow infer this directly from Youngian symmetry, and in particular, could you, following those lines, guess or, yes, get some hint towards more involved but still nice structure for higher point integrals, which is very much needed because for higher point correlators?
Yeah, that's actually something we are currently also trying to better understand in 1 and 2D first. I think these are really instructive models. It's, of course, simpler to work in lower dimensions, but the structure is still very similar. And at the moment, I can tell you that there are certain determinant relations coming from this Calabi-Yau business. We are still trying to systematize this and see how it relates to Basso-Dixon. Because, as you know, the Basso-Dixon formula in 4D and your 2D version, they are also somehow qualitatively a bit different, right? It's different integrals appearing in the matrix. So yeah, one has to understand the general framework.
Okay, I think there was a quick question from Kolya, and then we will.
How did you know it was quick?
In that case,
so a bit naive question. So I understand correctly, the integrals are annihilated by all elements of monodromy matrix, essentially, right? That's the statement. So can you then?
There are eigenstates of the monodromy, yeah.
Say again?
They are eigenstates of the monodromy matrix.
Yeah, so then there are also eigenstates of transfer matrix, but with whatever twist you like, right? So you can put any twist. So can you, well, for each of those, there is, I suspect it would be also highest weight probably spin chain, this transfer matrix, right? Is it? Then can you use some algebraic Bethe Ansatz to build eigenvectors and restrict to 0 eigenvalue sector somehow and find vectors which don't depend on twist? So, just more standard integrability.
You should tell me. I don't know. Of course, it would be nice to further look at what, how you can use integrability efficiently to compute these things. I think one difference to, say, two-dimensional setups where you have Youngian symmetry, say you have a scattering matrix that factorizes into 2-to-2 scattering matrices, typically you really just have to take a matrix product of two 2-to-2 scattering matrices. Here, the product between the scattering matrices is actually the integral, right? So you glue them with an integration vertex. So maybe the most complicated problem is to do to evaluate the product of these matrices. So I think this is a qualitative difference. Yeah, in 2D you would say if you know that the scattering matrix factorizes, you just have to multiply matrices. But here you have to do would still have to do the integrations just on a abstract level. Or maybe we can discuss afterwards.
Yeah. Okay. So I think with that, let's thank Florian again. And we are going to have a slightly shortened coffee break of 20 minutes. Okay, so welcome back. Remember to keep your mug safe. And I think the equations and Marcos are back. So Marcos will talk about resurgence and renormalons in integrable QFTs.
Okay, thanks for giving me this second opportunity for my talk. So I will talk about resurgence and renormalons in integral quantum field theories, and this is work with my postdoc Ramon Miravillas and my student Thomas Reis. Okay, so we work on integrability because integrability gives us exact and non-perturbative answers for observables in QFT. But this is rather an exceptional situation, and in generic situations we still use perturbative series to obtain asymptotic expansions. So the kind of observables that we compute in many quantum field theories are, so, for example, ground state energies, and they are given by functions of the coupling constant G. And perturbation theory doesn't give us exact answers, but it gives us asymptotic expansions. They give us asymptotic series in the coupling constant G. Okay, let me see if I can. They give us asymptotic series in the coupling constant G, and we know that these perturbative series are not the full answer. In general, in quantum field theory, on top of the perturbative series, we also have non-perturbative corrections. And non-perturbative corrections have a different mathematical structure. They involve exponentially small terms in the coupling constant of this type, an exponential of minus some quantity divided by the coupling constant, and these type of terms are invisible to perturbative series like that. So, in general, we expect that in quantum field theory, a physical observable will be given by the sum of a perturbative series plus an infinite series, possibly, of exponentially small corrections. And this is actually the answer that is suggested when you do a saddle point approximation to a path integral. When you do a saddle point approximation to a path integral, you will get typically the contribution of the leading saddle, which gives you a perturbative series of this structure. And then you can have subleading saddles with non-trivial actions, and this gives you this type of exponential here. And when you do the expansion of the path integral of a non-trivial saddle, you will get an additional non-perturbative series around this additional saddle with a constant c, and then some prefactor g to the minus b, and then another power series here. Okay? So the fact that we organize our life as perturbative series plus non-perturbative corrections is actually what the path integral suggests in many situations. Now, the formal object, so if you want to really combine a perturbative series plus exponentially small corrections, you have to introduce a new mathematical object. And this mathematical object that combines both types of terms is known in the mathematical literature as a transseries. Okay? So a transseries is just a generalization of perturbative series, including non-perturbative corrections. Now, making sense of these objects is very subtle. Why? Because the perturbative series, the asymptotic expansions to observables in quantum field theory, are actually divergent series. The coefficients grow factorially, so this series has zero radius of convergence and is not really mathematically defining a function. And actually, one can see that when one does this type of exponentially small corrections, the series appearing here are also factorially divergent. Okay? So, in principle, this answer is purely formal. You don't know how to extract numbers out of it when I give you the equations like this. There are, however, resummation methods which are very powerful and which were developed in a very general framework called the theory of resurgence, which make it possible to resum all these divergent series under mild conditions and produce actual numbers. I'm not going to give you the technical details of this procedure because I don't have enough time, but there are such methods to produce numbers out of divergent series, and this actually happens under very mild conditions. So usually you can produce numbers out of the series appearing in quantum theory. Okay? These are just additional exponentially small corrections with bigger exponents here. Okay? So usually you have an infinite series of exponentially small corrections. Okay? So this is just the first exponentially small correction, but there could be, for example, something proportional to e to the minus 2a over g. Okay? Yeah, there could be also other a's. There could be other a's with bigger real part or something like that. Okay, so in principle, you expect a very complicated series, a very complicated structure of non-perturbative corrections, which you order essentially by the strength of this number a. Okay. Nothing is obvious here, okay? Nothing is obvious, of course, you know. You need a theory to do this, right? Well, as I said, there are higher exponentially small corrections, which can be multiples of this, and there can be additional actions involved in the game, and so on, okay? So I think this formula is quite illustrative, but it's definitely not a complete formula. We would have to introduce additional things. But hopefully this will be clearer with the examples I will show later in the talk. Sorry? Trans-series are formal objects, so in principle there should be a choice of constants here. There should be a choice of constants such that you recover the exact answer of this observable in a unique way, with a unique choice of this constant C, okay? But trans-series are usually parameterized by these numbers here, okay?
So on the way around, given E of G, is it always, if trans-series exists, is it unique?
Well, yeah, it's unique. I mean, when it exists, let me show you the conjecture that I will give you here. So this kind of idea suggests that in a quantum theory, observables with an asymptotic expansion can be computed exactly by an appropriate resummation of a given trans-series. Okay, this means that the trans-series is unique. And the trans-series is obtained by adding appropriately exponentially small terms to the asymptotic expansion. So you have to start with the asymptotic expansion, which is obtained in conventional perturbation theory, but on top of that, you have to add exponentially small terms, which are these non-perturbative effects. And this is what we call the weak resurgence conjecture in a paper with Lorenzo Di Pietro, Sverbeglieri, and Cerone. And what is the appealing aspect of this conjecture is that it gives a generalized semi-classical picture of observables in quantum theories. So it means that you can decode an observable in a quantum theory by adding a perturbative series and these non-perturbative corrections. And actually, this conjecture is actually known to be true in, for example, many examples in one-dimensional quantum mechanics. Now, the idea, the kind of program is to see if this type of conjecture is valid, for example, in realistic quantum field theories or in toy model quantum field theories, so beyond quantum mechanics. And to test these conjectures, we need the ingredients. So the ingredients for testing this conjecture are the perturbative series and the non-perturbative corrections. And of course, we know how to obtain perturbative series. This is what we learn in graduate courses in quantum field theory. But the question is, how do you actually compute exponentially small corrections in quantum field theory? That's a kind of non-trivial question. And this is the subject of my less transparency. So what is the physical origin? The first thing you should ask in order to compute these exponentially small corrections, what is the physical origin of these exponentially small corrections? So there is one obvious source for exponentially small corrections in quantum theories, which are instantons. And instantons are non-trivial classical configurations which lead to additional saddle points in the path integral. So in principle, if you expand the path integral out a non-trivial saddle, you will get an exponentially small correction, which is the kind of answer that we saw before. And historically, instantons were regarded as the building blocks of these mathematical trans-series. And they actually are the building blocks of trans-series in many examples. For example, in quantum mechanics and in some supersymmetric theories. So one could think that one can actually reconstruct quantum field theory by combining perturbation theory plus instanton physics. But this actually turns out not to be true. And this was a very important discovery in the 19th and 80s, that there is a new source of exponentially small corrections in many quantum field theories, and this source of exponentially small corrections was baptized by the name of renormalons. So renormalons was, I think the name was found in a way as something similar to instantons, because it was thought that renormalons will share many properties of instantons. So renormalons are very mysterious. I'm going to characterize them by 2 or 3 properties here. And the first property was conjectured actually by Parisi and Toft, and they were focusing on these exponentially small corrections in asymptotically free theories, so at infinite volume. So what they conjecture is that renormalons are sources of exponentially small corrections, and these sources of exponentially small corrections, according to them, would have an universal form. And this universal form would be an exponential or minus an integer number over twice beta 0 in absolute value, which is the coefficient of the beta function, and g. Now, if you look at this formula, it looks very much like one instanton correction in which the action of the instanton would be 1/2 times beta 0, okay? And D would be something like the instanton number. Now, in an asymptotically free theory, this type of correction will give you what is called a power correction. So a power of lambda over mu to the a power of D of lambda over mu. So lambda here is the dynamical scale of the asymptotically free theory. And you see that when mu is very large, these are small corrections, okay? So these are called sometimes power corrections for people working in QCD. And the idea would be that these are like instanton corrections in the sense that there is a minimal contribution, which is 1/2 times beta 0, and then there will be integer multiples of it. And this was the idea they were considering. So I didn't tell you what is the origin of these things, but let me first give you another property they have. Well, the other property they have is that these exponential small corrections are actually more important than instantons. And this is typically because the strength of this exponential is bigger than the strength of an exponential corresponding to an instanton. And one way of seeing this is actually to consider the Larsen limit of these theories. When you consider a theory in which there is a Larsen limit, it turns out that these exponential small corrections survive the Larsen limit. This is known to be this is actually not the case for instantons. If you have an exponential small correction due to an instanton, typically it will disappear in the top limit. But renormal corrections are not like this. And this is precisely because beta 0 typically scale like n. And then this exponential small correction actually goes like e to the minus 1 over lambda, where lambda is the top parameter. So these exponential small corrections, in contrast to instant corrections, survive the large n. And the last property of renormals, which is important, is that they do not have a known semi-classical description. Instantons are somewhat easy because you just look at saddle points of the path integral, you span around them, and you have your instanton contributions. Renormalons do not correspond to non-trivial saddle points. So they are very strange objects because they are corrections to the asymptotic series, which comes from, if you want, from the trivial saddle point, but they do not have a known saddle point description. Okay? And this is what they are different from instantons, which have a semi-classical description. So if you don't have a semi-classical description, how do you detect such an exponentially small correction? Now, the key idea to actually find that these objects exist is to use a connection between the large order behavior of the perturbative series and the existence of non-perturbative corrections. And this is one of the key ideas of the theory of resurgence, that there is such a connection between the perturbation theory at a large number of loops and exponentially small corrections in quantum field theory. And I'm going to kind of summarize the result for you. This is actually something that can be shown in one page by using techniques of resurgence and Borel resummation. But the main idea is that if you know how the perturbative series behave at a large number of loops, you can predict the shape of this exponentially small correction as follows. As I told you, an, these coefficients grow typically factorially. But when you study the precise asymptotics of these coefficients, you can refine this factorial growth into a gamma function, gamma n plus b, and a subleading exponential growth of the form a to the minus n. So typically, all the perturbative series that you find in quantum theory are going to grow factorially exactly in this form. And you see that this involves two additional parameters, a and b. Now, the result I want to quote is that if the perturbative series diverges like this, then there is going to be an exponentially small correction in which a is going to be the weight of the exponentially small correction, and this b is going to be the prefactor of the coupling constant in front of this exponentially small correction. So this means that if you know how the perturbative series grows factorially with precision, you can actually predict the existence of non-perturbative corrections. Of course, in some cases, these non-perturbative corrections are due to instantons, but in other cases are going to be renormalons. Now, how do you obtain information of the perturbative series at very large number of loops? So this is actually a very hard problem because it's hard to push perturbative series in realistic theories to very high order. Now, some people have tried to do this by numerical methods. For example, you can work in lattice perturbation theory, and for example, Bauer, Bali, and Pineda in lattice QCD, they were able to obtain maybe 40 terms of the perturbation theory of some observables, and from this they could extract the coefficients A and B numerically. Another option to actually detect this large order behavior of the perturbative series is to work at large n. And the nice thing of working at large n is that the diagrams get order by powers of n, and then you can see that the leading contribution for at large n in renormalizable theories and many quantum field theories is of bubble-like diagrams that look like this. And if you focus on the large order behavior of these diagrams, you can actually produce reliable estimates of these coefficients A and B numerically. And this has been essentially the main method that people have used to detect renormalons in asymptotically free theories. So some limited information has been obtained in this way. Now, what is the role of integrability in all this? Well, many asymptotically free theories in 2 dimensions are integrable. The S matrix is certainly known, and this includes important models like the O and sigma model, the Gross-Never model, and so on. And the key question is, can we use these models to obtain information on renormalons? Okay? So far, integrable models have not been very much exploited to obtain information on renormalons, and the idea to try to clarify what is the role of renormalons in asymptotically free theories is to look at integrable models. Now, in order to do that, we have to do something very unnatural, essentially, which is to take the exact answers provided by integrability and decode them in the form of a perturbative series plus exponentially small corrections. And this is very unnatural in many contexts because in many cases, not even perturbative series are easy to extract from, for example, the answer given by the Bethe Ansatz. And this was already noted in the founding paper by Leaf and Lineker, in which they noted that using the exact Bethe Ansatz equation for the ground state energy of the Bose gas at gamma equals 0, here gamma is the coupling constant, so producing the perturbative series was so hard that it was actually even better to use dietary perturbation theory. So the Bethe Ansatz answer is very often very unnatural to obtain some perturbative information from it. And this has been essentially a problem for making the connection between Bethe Ansatz solutions and perturbative theory. Now, here in the remainder of this talk, I will focus on a very particular observable of integrable field theories in 2 dimensions that you can study from many perspectives. In particular, you can find its exact expression using integrability. And this is the ground state energy of the 2D integrable model once you couple a chemical potential H to a global conserved charge Q. So essentially, you take the Hamiltonian of the model, you add H times Q, where Q is a conserved charge of the model, and then you take the trace of this operator, you take the logarithm, you divide by the volume, and the volume in space-time, and then you define this, this quantity I will call the free energy. Now, the role of this chemical potential is very important because remember that I want to obtain something that I can understand in perturbation theory. And if I have an external parameter H, I can exploit asymptotic freedom because I know if its H is going to be very much larger than the dynamical scale of the model, I will be able to use perturbation theory thanks to asymptotic freedom. So actually, this observable in this regime will have a perturbative series, an asymptotic expansion in powers of the running coupling constant G at the scale set by H. So this is something that you can compute in perturbation theory. It's hard to compute it, but you can do it at the very first orders. And in some cases, large n, you can do it even at very large loop order. Now, on the other hand, you can study this observable by using integrability, using the Bethe Ansatz. This was pointed out by Polyakov and Bigman long ago. So essentially, you have to consider a Fermi density of Bethe roots, epsilon theta, which satisfies an integral equation of this type. So in this integral equation, you can see that this Fermi density is going to vanish at the endpoints. And then here you find the chemical potential H, and then here M is the mass gap of the theory. Okay? So it's actually the mass of the particles which are essentially condensed by the action of the chemical potential H. And the kernel of this integral equation can be computed from the S matrix plus an ansatz of what are the particles which appear when you turn on this H. H is a chemical potential. When you turn it on, there will be a density, non-trivial density of particles that appear, and these are the particles whose mass is given here. And then once you solve this equation, you can compute this free energy by just using this equation here. So this is an example of the thermodynamic Bethe Ansatz, and this gives you an exact expression for f of H. Now, you have then the possibility of studying this observable both in perturbation theory and exactly. Okay? And the question is, can we use this observable as a proof of renormalence in asymptotically free theories? Well, the question is how you would detect renormalence in these quantities. So remember that, as I told you, there is one possibility, which is to study the perturbation theory of this observable at very large loop order. And this is hard indirectly in perturbation theory. There was a very beautiful result by Dimitrov Volin, which actually made possible to extract very long perturbative series for FH directly from the Bethe answer. So the work of Dimitrov was very important because he actually broke this kind of limit that was set by the Bethe Ansatz in terms of obtaining perturbation series. So there was this abstraction that was already noted by Leaf and Liniger of obtaining perturbative series from the Bethe Ansatz, and essentially the work of Dimitrov made possible to actually break this constraint. Now you can produce then very long perturbative series, and you can now study this series numerically to try to see if there are renormalons there. This is some work I did with Thomas Reis, and also there was very impressive work here done in Budapest by Zoltán, János, Arpad Egedus, and their collaborators. And actually, when you do this, you confirm that exactly you have a first renormalon correction as predicted by Parisi and Toft at exactly the value d equal 2. So you have a quadratic power correction that is confirmed by this numerical analysis. And this was important because people were not completely sure if this renormalon correction would exist, and this gave a very kind of clear confirmation. One can also work at large n, either diagrammatically or using the Bethe Ansatz, and one can also obtain some results in this way. But these two approaches to the renormalon problem in integral models have a problem, is that either you work numerically and then higher exponential corrections are hard to see because when you work numerically, the smaller the corrections, the harder it is to detect them. And to work at large n, you don't know if what you are obtaining can have like non-trivial 1/n corrections, and this is also important. So what we try to do is to actually extract these exponentially small corrections from the Bethe Ansatz exactly at finite n, without relying on numerics, not on large n approximations. And this is the result that we obtained last year. And actually the way to do it was to exploit an old method to understand the Bethe Ansatz equation, which was the Wiener-Hoff method. And this was a method that was already obtained before in order to extract perturbation theory from the Bethe Ansatz. And I want to mention here the work of two Hungarian physicists, Hasenfratz and Niedermayer, who did very important work. They were actually able to calculate the mass gap of the theory as a function of the dynamical scale exactly in their work. There was also work of János on the principal chiral field. But in this work that it was done in the early 90s, people were interested just in perturbation theory. And they were neglecting precisely all these exponentially small corrections. Now, in integrability, people have actually looked at these exponentially small corrections in the Sine-Gordon model. There was very nice work by Samolochikov. And essentially what we did was generalizing this work of Samolochikov to asymptotically free theories. And that is highly non-trivial because in the work of Samolochikov, if you are familiar with it, essentially all these exponentially small corrections come from poles. And the crucial mathematical aspect of asymptotically free theories is now you have branch cuts together with poles, and this is actually the signal of renormalence in this kind of things. So there are no renormalence in the Sine-Gordon model, and it's only when you go to asymptotically free you will see these branch cuts which signal renormalence. And once you do this, you can actually obtain fully analytic results for these exponentially small corrections. Now let me just give you a very sample answer. For the O3 sigma model, we find that this FH has a perturbative piece, and then you have an exponentially small correction, which multiplies a non-trivial power series here. Notice that some of the coefficients of this series can be complex, but this is part of the mathematics of transeries. The coefficients can be complex. And then you can push the calculation of this power series that multiplies exponentially small corrections quite high. And this actually was done by the Budapest group, by Zoltán, János, Egedus, and Bona in a recent paper. So you can actually find reliable finite n results for these non-perturbative corrections in these integrable models. Now, yes? Sorry?
It's plus minus, right? So, but there's
yes. This is actually something that I didn't have the time to explain. The thing is that this series is divergent. Okay, so you have to make sense of this series by doing what is called lateral Borel resummation. And in doing lateral Borel resummation, you have to choose an integration contour either above or below the real axis. And then you have to make a choice of what is your direction of resummation for the perturbative series itself. And this choice of lateral Borel resummation is correlated with this plus minus sign here, in order that the final result is real. So this is one of the part of the kind of subtle aspects of transeries. The coefficients can be not only imaginary, but actually ambiguous, and this ambiguity is related to your choice of Borel resummation. In other words, the coefficients appearing in transeries are not intrinsically defined. They depend on your choice of lateral resummation in such a way that at the end of the day, nothing depends on your choices, and you get a unique real answer. Okay?
But shouldn't you then have also a plus minus on the F per?
Sorry?
Shouldn't you then put a plus or minus on the F?
Yeah, there should be, but here you kind of understand this because this series is asymptotic. So this is just like a remnant of your resummation procedure for this series. But this is actually quite common. If you see table formula for the AD function, you will see the same kind of notation. The AD function also has this sort of phenomenon, and you also see that you will have plus or minus signs that are understood to be related to the Borel resummation of the original perturbative series. Okay? So it's sort of a standard for asymptotic series and corrections. So perhaps what is nice about this approach is that in principle gives you all exponentially small corrections. Now, this is very beautiful because these exponentially small corrections, as I said, they are turned out to be related to the poles and branch cuts of the kernel of the Bethe Ansatz equation. And the most striking consequence of this method is that there are corrections which are not of the form predicted by Parisi and Toft. Parisi and Toft told you that this correction should be an integer divided by beta 0 times g. Okay? An integer divided by twice beta 0 times g. But actually, when you do the exact analysis in integrable theories, you find that there is a non-trivial correction here, 1 minus r in the denominator, and this correction actually vanishes, depends on the model. So this is the value for the Gross-Nevet model, and this is the value for the principal chiral field. But you see that this vanishes at large n, but is non-trivial for finite n. So the Parisi-Toft conjecture is valid in the large n limit, but it's actually false at finite n. And this is actually one of the useful aspects of being able to work at finite n, because at large n, you wouldn't see this correction. You would see some sort of exponentially small corrections that would essentially kind of fuse together, okay, when you work at large n. But at finite n, you can see that there is a finer structure in the exponentially small corrections. So we obtain, these are actually renormalon type of corrections, but we also obtain instanton-like corrections. For example, what I showed you in the O3 sigma model, this exponential correction is probably due to instantons. And in general, in the ON nonlinear sigma model, we find a leading renormal singularity plus corrections of this form, and you see these corrections will survive the large n limit. So these are probably instanton corrections, because here you have an n, here you also have an n, so this will survive, and these probably are due to non-unstable instanton corrections in the ON nonlinear sigma model, but this is again a conjecture. One should actually work harder to try to understand this. So one actually can verify, so all these corrections are very nice, but one can actually even go further and check that these corrections actually control the large order behavior of the perturbative series as expected from the theory of resurgence. Remember that I told you that there is a link between exponential small correction and perturbative theory a large number of loops. And this is a strong check that the results that we have obtained are correct, and we were very careful in trying to make this connection precise. And in addition, all the available evidence we have indicate that exact results for integrability can be recovered by resumming the resulting transeries. So this is in agreement with this resurgence conjecture that I presented you at the very beginning, that you can recover exact results by going beyond the asymptotic expansion given by perturbation theory and adding systematically these non-perturbative corrections. I have to mention here that in the work of Zoltan and Janos, in the O4 sigma model, this was tested really with huge precision because they were able to obtain 2,000 terms for the perturbative series. And then this means that they could do this check in kind of very precise, with very precise numerical precision. And let me actually point out that as far as I know, these are the only available analytic results on exponentially small corrections at finite n in non-supersymmetric quantum field theories. I mean, there are other models, like for example, two-dimensional QCD, where you can get similar results, but in asymptotically free theories, I think these are the only available analytic results. And as I said, this already gives you counterexample to this Paris-Titov conjecture. So let me come to the conclusions. So I think the most important conclusion here is that conventional perturbation theory should be replaced by resurgent perturbation theory, in which you have to complete perturbative series by adding these exponential small corrections in the form of this new mathematical object called transseries. And this framework seems to be powerful enough to include realistic quantum field theories. I have to say that people working in QCD have been doing these kind of things for many years, but of course you have many limitations about foundational aspect of renormalance in QCD because we don't have all these techniques, and the idea was precisely to use integrability to actually shed light on these foundational principles. But in principle, this framework should accommodate even QCD and Yang-Mills theory. Now, I think also a very important thing is that it's just a kind of declaration of ignorance. We do not really know how to compute exponential corrections to perturbative series in QFT. So you take your favorite textbook, it will tell you how to compute the asymptotic expansion in full detail, but we don't really have general methods to compute exponentially small corrections. Instanton calculus was developed historically as a way to supplying this. But instanton calculus already in itself is quite difficult. Even if you have a semi-classical picture, it's very difficult. We know that sometimes it breaks down due to infrared problems. But renormalons are even more subtle than instantons. They are not described by shadows of the path integrals. And for example, if I wanted to calculate the renormalons for FH directly, I wouldn't know how to do it. There is no recipe in the books to take the Lagrangian of the ON sigma model and compute the renormalon corrections from it. There is no recipe in the books. There is no such a renormalon calculus. Now, integrability makes a difference. It actually helps us to understand this problem because it gives you analytic results from the Bethe ansatz for exponentially small corrections in these asymptotically free theories. And this vindicates the renormalon picture, but with some subtleties. It makes it also more complicated. For example, this Paris-Titov conjecture, which tried to predict the general pattern for these renormalon corrections, turns out to be just a Larsen approximation. And then an obvious question is, could we have a more general conjecture describing all possible exponentially small corrections in asymptotically free theories? So this is still an open problem. Some people, like Martin Lusser, for example, think that you won't have a general pattern. This is just observable dependent, and you can have all kinds of things. But maybe there is a more kind of general conjecture. And in a sense, the most important open problem is to be able to calculate these transitions from first principles, in particular for renormalons. So these are really completely unexplored unexplored sectors of the path integral of asymptotically free theories. And what I find very interesting from the application of integrability is that integrability is able to predict these corrections, so this will be a signpost for any future renormalon calculus. If somebody, I hope, will find a way to do renormalon calculus in asymptotically free theories, at least the results of integrability will give a signpost for this renormalon calculus of the future. So this is my last transparency. Thank you very much for your attention.
Okay, thank you, Marcos, for that very nice talk. I think more equations was better in this instance. Questions? Kolja? Sorry, Kostya.
So it's quite remarkable that it's very interesting that you find this deviation from the Paris-Titov formula. Do you have a diagrammatic explanation of this 1/n shifts in the exponent?
Well, you can actually see that this should actually give 1/n corrections to the diagrammatics. Yes, we don't have a direct calculation because you have to go to next to leading order, so you have to consider corrections to bubble diagrams. But this should have a diagrammatic explanation. This is actually a very good question because people. What is interesting is that people thought that 1/n corrections wouldn't change the location of the Borel singularity, right? People thought that this would correct. But what we find is that 1/n corrections actually split the renormalon singularity into two. And this is actually the new phenomenon that was, in a sense, missed by the traditional approach. So people thought that 1/n corrections wouldn't change wouldn't change the strength of the exponentially small, but just give corrections to the power series, but they wouldn't think that it would split the singularity. So
it becomes a cut?
No, just in terms of singularities in the Borel plane, this means that at the leading singularity at large n, when you include finite n corrections, it splits into two. Okay.
But they are still poles.
No, they are in general they are branch cuts, both of them.
Shota?
So if I understand correctly, this is renormalons are for infinite volume.
Yes.
And do you have an idea like what happens if you put the theory on a finite volume?
Well, in finite volume, that would be very interesting to develop. I think there could be still something like renormalons because you know, the perturbative series is still going to be factorially divergent, and it's not clear that all the singularities, all the exponentially small corrections are going to have a purely semi-classical origin. This would be achievable, I think, also because these models, the ground state energy at finite volume can be computed with integrability. So this, I think, is one of the really interesting open problems to address in the future. It's clear that in finite volume there is more chances that instantons do the job, okay? But I think there is still some place for renormalons to play a role there.
Kolya?
So Resurgence connects the asymptotics of the perturbative series with, say, the first non-perturbative correction.
Mm-hmm.
But sometimes the first few perturbative coefficients are connected to the first few coefficient in the exponentially small correction by some bridge equation. If you have, say, a differential equation.
Mm-hmm.
So do you expect something similar here for these integral equations, ON or these principal models?
So that there is that you can extract the whole series with
I mean that you can relate the beginning of the perturbative series, not the asymptotics,
mm-hmm.
but the beginning of the exponentially small correction directly,
mm-hmm.
without going to the asymptotics. Like in these Eccles bridge equations, this is what you do.
I
exactly.
See, I see. Yeah. Yeah, I think, that's in a sense, that would solve a lot of our problems. If we had something like this for the integral equation, that would be fantastic. And this also would give a systematic way of computing this trans-series more systematic, but I don't know how to do that, yeah. That's again, another important technical problem to be solved, yeah.
Kolya?
So you know, in QCD at least, at finite temperature, the instanton decomposes into n lumps.
Yes.
So could those be kind of related to this?
Yes, that's actually, some people have thought that, you know, that the composition of instantons in fractons could explain this thing. But actually, the fact that you have now these sort of corrections makes life again more complicated. Because you see, this introduces an additional fact, you know, usually people will say, okay, you have d over n, essentially, and then you decompose your instanton in fractons, and here you are, this is a fracton. But now with this additional factor, this becomes even more complicated to be interpreted semi-classically, because you don't longer have d over n, but you have n times, you know, 2 over n minus 2 or n minus 1 over n. So this actually complicates the fracton picture of renormalons.
More questions? Oh, yeah, sorry. Just wait for the microphone. Yeah, okay.
If you say that it's not always clear how to compute them, is it at least clear that it's well defined? I mean, this trans series in all cases?
Now, trans series, you see, trans-series are well defined once you agree on doing a perturbative expansion. Once you have an asymptotic expansion, the trans-series that follows is well defined. But it's clear that trans-series, these exponential corrections are attached to the fact that you did a perturbative expansion. So these renormal corrections only have sense once you decided that your first approximation is going to be perturbative series. Okay? Now, in some cases, still these renormal corrections can give you physical intuition about direct observables. For example, if you are studying the energy gap of a superconductor, you can see that the energy gap of this superconductor is going to be essentially controlled by this type of renormal effects. So they actually give you power corrections, a qualitative window into power corrections in theories in which there are exponentially small corrections. So in that sense, you know, they actually help for actual physical quantities, like energy gaps.
I mean, what I meant is, maybe it was not completely clear, but like originally, Toft also showed some examples in simple cases. I mean, this sum over bubbles.
Yes.
But the sum over bubbles is in the end just some particular subclass of diagrams.
Sure.
I mean, some resummation of perturbation theory. And
yes.
That's why I'm asking whether it's really
no.
defined. One guy says, let's resum this, another says, let's
resum
that.
But I agree with you. I mean, you cannot select diagrams according to your wishes. These diagrams are selected by large n. So there is an extra parameter that controls. If you start like selecting diagrams, you could change the shape of the exponential small correction and so on. But once you take renormalized perturbation theory, which is uniquely defined, the asymptotic series is uniquely defined, then this actually defines already the type of transseries that you are going to obtain. So the transseries, as I said, once you have your asymptotic series set up, the transseries is pretty much defined up to overall coefficients. Now, the value of the overall coefficients of these exponential small corrections are very subtle because they depend on your resummation choices, but in principle there is a single choice of coefficients that reproduce the exact answer. So in that sense, it's a well-defined object.
More questions? So I had a question actually about, if we went away from field theories and to string theory,
yes.
D-branes, of course, famously are sort of instantons. Is there a picture where what renormalons might be in string theory?
Absolutely. Well, I think in string theory, of course, there are exponential small corrections, but as far as we know, they are the ones that we know are due to D-brane, so they are instanton type. Now, I don't know if there are renormalons in string theory. Okay. Now, renormalons are typically absent in supersymmetric theories. So, for example, there are no renormalons, say, in n=4 super-Yang-Mills. There are no renormalons in many extended supersymmetric theories. So, I don't think that in string theory, I would be surprised if there are renormalon effects. But there are instanton effects, and you can play the same game of relating the perturbative series to the non-perturbative correction, and these people have done in minimal string theory and things like that, yeah.
But what about non-supersymmetric string theories, or like a two-dimensional string theory?
Like C=1. Yeah, I wouldn't expect renormalons there, I would say. But this is more like a large N quantum mechanical model, right? So, there are no renormalons. Typically, there are no renormalons in quantum mechanics, so I wouldn't expect renormalons there.
Okay, thanks. More questions? If not, let's thank Mario. Yes. Okay, so our next speaker is Eduardo Vescovi, who's going to talk about correlation functions of determinant operators in conformal fishnet theory.
Thank you very much for this kind invitation. It's a pleasure to be here and present my work with Omar Shapo, a former master student in Imperial College and now PhD in King's College, London. It's a work about fishnets. So to get everybody on board, I just remind fishnets are models, quantum field theories, where endpoint functions are described by Feynman diagrams with the topology of a regular lattice. We're going to focus mostly our attention on the square bosonic lattice, underlying the biscalar fishnet theory. Here, the main protagonist is the fishnet vertex. This sets the basis for most of the properties, directly or indirectly, that this theory has. Starting from integrability, also in connection to an integrable lattice spin chain model. It is an integrability that really stems out of the diagrams. It is more direct and transparent than that in N=4. That, of course, underlines many techniques based on this integrability. It also ensures that the theory is a conformal field theory in 4 dimensions, so it is a rare and unique case in more than 2. and many other properties like the Youngian bootstrap that we have seen this morning. Actually, the fishnet itself, strictly speaking, is not conformal. You had to add double trace counter terms to make it so. These are the so-called minimal size effects. They enter these counter terms, they needed to be added, and they appear whenever you have len2 operators in the diagram. This is to stabilize the RG flow, to make this theory fully conformal. So this is the biscalar fishnet with only, as the name suggests, only two scalars corresponding to these sets of lines. It is a particular case of a more general fishnet, actually. I'm going to refer to that as three-coupling fishnet. People also call it chiral CFT4. Yeah, just a name to remind that it has three coupling constants, but more importantly, you're also allowing fermionic lines. So it is more complicated. You have three scalars, not only two, and also three fermions, and three coupling constants, not only one associated to a single vertex. And in turn, just to finish this review, it is, this theory is a particular limit of a more general theory, very well known, which is n equal 4 super-Ms with gamma deformations. If you go to a particular corner of the parameter space, you recover this beautiful fishnet. And again, if you can go back by setting two couplings out of 3 equal to 0, you go back to the biscalar fishnet. So the conclusion of this first slide is to make this question. So if all the physics of the fishnet is so encoded into the graph structure, how do we compute different observables? Let's focus on correlators. What you have to do is to carve out a finite size lattice along a certain curve. This will define a certain sequence of fields. This, for instance, will describe a certain single trace operator with this sequence of bosons, the phis and the psis, the fermions. These are the typical correlators that have been considered so far. The very general question that we started with the student was to ask what happens now if we consider operators that have they contain many operators that have a dimension that is not of order 1, like in this picture, where you have a dozen of fields, but instead it scales with some powers of n. And if you ask this question in n equal 4, you can have many choices. You have scaling like linearly in n or n squared. This corresponds to a variety of operators. We stayed very pragmatic, and we went for the first category, so linear scaling in n. And among this huge category of operators, we focus our attention on the determinant operators for reasons that I'm going to explain in the lower part of the slide. These operators are defined, as the name suggests, in terms of the determinant operators, determinants of scalar fields. I call it phi generically. These are local, engage invariant. You can expand them in components. The fields with the gauge indices are contracted not to Kronecker deltas to create traces, but they're contracted with epsilon symbols, so plus and minus ones. I denote with phi a generical combination of the scalars. The y is the so-called polarization vector. It is a 6-dimensional vector, an array of numbers. And whenever you take it to be null, these operators are 1/2 BPS in the mother theory, in n equal 4 super-Ms. They have been extensively studied also in holography. They correspond to maximal giant gravitons, D-branes wrapping an S3, stabilized by angular momentum, which is maximal, satisfies a bound. This is why they're called maximal giant gravitons. And the reason for revisit this story, these operators, stems in one motivation that I want to bring up, stems from an observation that in this paper with my collaborators, Yunfeng and Shota, we made in a paper years ago when we were studying correlators, 3-point functions involving 2 determinants and a single trace. There are certain cases in which this expression can be rewritten in terms of an integral of Q functions. This is an interesting observation because there are many other variables of subquantum level that can, in gauge theory in n equal 4, that can be written in this form. And it is so this gets added to an ever-growing list of such observables. And this form is interesting because it seems to suggest that maybe one can apply some sort of SOV method, separation of variables method, to obtain them in this form, indeed. In integrability, SOV is very popular because in essence it gives you a chance to have a full quantum control on your observables, because the Q functions are very well known and studied at finite coupling. At the same time, we also know from fishnets that we had a lot of developments coming from lower rank interbond spin chains, as well as the fishnet itself studying SOV. So in some sense, determinants may sit in a sort of sweet spot, and they can further advance the study of SOV. This is a long-term goal to keep in mind. I want to bring up two other motivations before starting. In literature, people have also constructed deformations of determinants by replacing a letter with a word, a product of fields, including covariant derivatives. That is to say, an open spin chain, you see from the indices. The spectrum is usually no BPS. People have studied these objects, also with integrability. This list of references is very conservative. There are many works in this direction over the years. And holographically, if a determinant creates a giant, these creates they add open strings and ending on giants. And there have been a series of papers where people have actually constructed explicitly the worksheet of these open strings, and they obtain a match and a map between the energies of strings and the anomalous dimensions of these operators in some larger charge limit where this matching is possible. Here the hope is that by studying operators and getting full control on them from the fishnet point of view, where this task may be possible, maybe we can also say something about the holographic duals and expand our dictionary beyond the current models that we have. The last point is more generic, is about large N quantum field theories. It stems from the analogy, the similarities that we have between determinants of scalars, with matter in the adjoint, and baryons, like in large N QCD, where you have matter. These are color singlets of quarks, so particles in the fundamental. Here, the objective would be to study these operators in these fishnet theories, where the graph content is particularly simple, and maybe hope to derive some systematic way of resumming the loop expansion. In a theory, again, we also have an handle on these correlators, potentially from integrability. This is a very broad perspective. Now, I want to start to tell you exactly what we have accomplished. So in the first part, I want to make some general questions about the perturbative structures of these correlators. Because if I told you that we had so many techniques coming from an equal 4, both in gauge theory and in string theory, now the question is, what are the additional challenges that fishnets pose to the study of these operators? So both in the mother theory and in the fishnets, it's useful to refresh our memory and remember that determinants as heavy operators lack a standard notion of planarity, the usual expansion in ribbon graphs. This is easy to understand if you compare the two-point function of single traces and the two-point function of determinants. These two-point functions are protected, of course, but that's not the point I want to make. I want to make comments about the large N expansion that is applicable for all states, also in the fishnet. So when you have traces, of course, you know that the trace naturally defines an order among the fields. So the leading N contribution is simply a planar diagram. You have to draw all of them. This ensures this is leading in N. For determinants, the story is different because there is no naturally an order. They are defined by epsilon tensors. You can swap fields. The worst thing that can happen is getting a minus sign. You can, of course, decompose them onto traces, multi-traces, but the catch is that they would belong. So to the leading order in N, there would be both planar and non-planar diagrams contributing. This is a very well-known fact coming from the early days of IGST and these heavy operators, as well as large N QCD. So there are combinatorial effects. There is another combinatorics, huge combinatorial factors that non-planar diagrams carry, positive powers of N, and they usually overwhelm the natural 1/n suppression of non-planarity. So these diagrams come up in N, and they contribute to large N. This is not a big deal in N equal 4. It is hard combinatorics. But what happens instead when we go to the fishnets? Because as I said briefly at the beginning, the conformality is well established only for the planar fishnet. So what does it mean? Does it mean that we have to, that these correlators of determinants would lose their conformal properties? Does it mean that we have to first preliminary study the renormalization of the theory beyond the large n limit, more fundamental first principle problems? And the answer to these questions turns out to be negative if we think a bit more carefully about the expansion of these correlators. Let's focus on, again, on a generic example. I will have some graphs of some specific correlators at the end. So let me denote the scalars with the generic names. This also applies, some considerations also apply to the mother theory. The way to answer that question is to proceed with some methodology, some wise methodology, to carry out the weak contractions. Suppose that you just have a determinant pair. You can first operate the free weak contractions among the scalars over here. And if you do that, well, you can operate all the weak contractions and obtain simply the tree-level two-point function. That is not super useful because this would lead to some disconnected contribution in a higher point function. But anyway, the contribution stays there. Or you can instead operate n-1 weak contractions between the determinants. So this leaves a pair uncontracted that gets organized into a single trace of length 2. Or you can also have longer contributions. Suppose that you only take n-2 contractions. So 2 contractions are left. So you have 4 fields from the determinants left uncontracted, and they organize into these length 4 contributions, a single trace and a double trace. And the same play can go on. The key observations here are actually 3. One will be useful for later. You see these intermediate states have these projections, have an alternating structure, 5-5 dagger. So you have always a scalar from the first and a scalar from the second. And the pattern repeats also in longer traces. This will be useful for later when we will consider some actual diagrams. For now, the considerations are, the key observations are 2. One is that all these terms carry uniform powers in n. There is no enhancement that one trace would have compared to others. And all these traces are short. So this is the actual traces that we have to consider are short traces. And this is useful in the second part when we finish off these contractions. For instance, when we overlap this pair with this length 4 and also with interaction vertices. We are in a fully interacting theory. At the end, we only have to consider short traces. So the conclusion is that after these wise contractions, you realize that from the bulk point of view of the graphs, we're going to say something about the boundary later, but about the bulk topology is the same planar fishnet in the common traditional literature. It is to say, regular lattice structure, potentially decorated with the planar counter terms, but these are the usual planar counter terms that I said at the beginning that ensure the conformality of this graph. So they have, of course, the same property of finiteness, conformality, and also integrability. So this potentially paves the way to use integrability for these operators as well. While I still keep this picture, I make a few other comments. I don't want to sell the idea that, nevertheless, this method is convenient from a practical point of view. That is to say, really with pen and paper, or even with the help of a calculator, for a number of reasons that also marks a difference with the traditional literature of fishnets. First, notice that here the lengths of these intermediate states are not fixed. This little l, that in this case was equal to 4, this state up here, this index is a running index. You may have different contributions, and a priori, just by looking at the correlator written on paper, there is no really way to understand which of them, if one or more of them will contribute. You have a bit to sit down and empirically work out what are the intermediate states that may enter. It is not said, as the picture may suggest, that if you have a certain length of an external state, this will uniquely fix the length up here. You may have different contributions. We'll have an example later. And a problem related to that is that you will also, since L is running, you may also have L equal to 2 over here, so this term over here. And this will imply that on general grounds, you don't really have a direct way to exclude from the get-go the appearance of double-traced vertices. I stress, these are the good double-traced vertices. This is different from the traditional literature of fishnets, because usually what we do in most of the papers, if we want to go to some simplifying limits, we don't want to consider lattice impurities. We simply set the lengths of the operators all greater than 2, and we will have the wonderful regular fishnet. Here, potentially, there are always minimal size effects behind the corner that may appear. The third point is related to the complexity of this procedure. Going to the three-coupling fishnet or considering determinants of combinations of scalars will bring a complexity that is beyond normal control with a proliferation of diagrams. So while it is technically clear, it is in practice complicated to carry out. And for that reason, I want to explain an approach that was already in the idea and in some form in the paper with my collaborators. But we expanded this method in 2 directions. Before I present it, I want to say what are the improvements so that we can see them in the next slide. So in this method, we are going to, of course, bypass all the technical limitations. What are the changes with respect to the past? We have a method that can include all the interaction vertices, potentially an arbitrary number. It is only limited by computational power. So this generalizes the approach that in the original paper was only at 3 level. And the second is that we implemented the formulas that I'm going to show in an algorithmic way in a mathematical script. So you can input your external states, press Shift-Enter, and this will produce the corresponding diagrams. I'm not going to go through the derivation of this method, but at least I want to tell what is the flavor and also how it can be applied beyond fishnets potentially. So the idea is to rewrite the correlator of determinants in an alternative form that is more manageable. Rewrite the quantum field theory path integral as a matrix integral with auxiliary degrees of freedom, and integrate out the physical degrees of freedom in some careful way. What are the degrees of freedom first? You have bosons and fermions. You have this row matrix, which is an m by m matrix. The size is determined by the number of determinants. And you also have a row hat, which is a sort of element-wise rescaling of row. This carries information about the polarization vectors and the positions of the scalars in 4 dimensions. I also stress that this matrix is constant, so no space-time dependence. So in this will be a matrix integral, not a QFT path integral. Likewise, the same comment for the xi's, xi bar and xi. These are auxiliary fermions, and you have, if you look at the indices, you have a pair of them for each determinant. The reason is simple to understand, because in one of the steps you need to trade the determinants for Gaussian integral, for Grassmann integrals. So you need a pair for each of them to play this game. I want to flash what are the ingredients inside. So you have an action that is quadratic, and it has also some non-linearities. It is simple to solve because it carries a power of n in front. So you can do saddle point expansion. And by the way, in fishnets, we are precisely interested in the large n limit. So really, this is not an approximation. This is what we want to do if we want to stay in the conformal fishnet. And the super interesting part of the integrand is this prefactor. If I have to describe it in words, I would say it is a sort of the multi-trace O of short length that I put here, but surrounded with all the possible, with a cloud of all the possible interactions before actually these interactions connecting to the determinants. Mathematically, it is defined by this quantum average. This is how the degrees of freedom are, the physical degrees of freedom are integrated out. If not for these shifts, So the scalars in the multitrace are shifted by these matrices S, I will say later who they are, and also in the interacting part of the Lagrangian. So Yukawa, quartic vertex, and double traces, but not in the free part. This comes from some Gaussian integration that you have to perform, some shifts that get eliminated in the free part. This object, this is the first improvement. This object is fully defined at finite coupling. Of course, to calculate this object, it is very prohibitive and daunting to do, actually, at finite coupling. So the strategy will be to expand it perturbatively. I will make another comment on this O. First, I want to say who is this S. So S, the S's are matrices. They have an index J, so you have S1, S2, S3, because you have the three scalars. And they are matrices with indices A and B that come from this product chi bar, which is not a bilinear. If you got lost at this point, I just want to tell that all in all, in this matrix integral, you just have a rho appearing. This is the only integration to do in the last step, because this O, despite depending on this sort of classical backgrounds, these S's, so on these fermions, the fermions are integrated out via some Feynman rule, via this fermionic average that appears in here. So this is perfectly calculable and implemented in an algorithmic way. It can also be generalized for other operators. I will say something later. The final comment before transitioning to the next slide is to remember that in the previous paper where we studied certain 3-point functions, it was exactly this object, OS, that could be rewritten into some nice form. We were studying 2-point functions of two determinants and a single trace. And in some cases, we could rewrite this 3-point function, which is essentially this piece, as an overlap between a convenient matrix product state and the spin chain state corresponding to the single trace. And this was leading to some considerations about the integrability of a pair of determinants as an integrable boundary state. I mentioned this in connection to the previous paper. We didn't do any investigation of this kind in the publication, but certainly this would be the point to start with, also for the things that I'm going to say in the last conclusion. Okay. M is a convenient matrix that contains, again, information on the y's and the x's. So it has a certain definition coming from those. Yeah. This is just a rewriting of the result into this nice form, expanded form as an overlap. All right. Again, if this is confusing, maybe let's say, what can we do with that? Can we just work with determinants? Can we do something else? What is the actual output if you have to use it? So not only we can study determinants, but we can also play a little bit with the polarization vectors and consider some deformations of determinants. This is a procedure that was used, for instance, in this paper about 4-point functions to control the flow of R charge in certain channels of the 4-point function. And the idea is simple. If you consider a determinant of phi 2, so an array of phi 2s and phi 2s, and you want to replace one letter with phi 1, you can prepare this state and then take a derivative with respect to A1. This will pick up one phi 1, and then when you set A1 equal to 0, you will eliminate A1 together with phi 1 in all the others, so only phi 2 will remain. So we can consider also this with the current technology. And we can have a look at an example. If we take these two deformed determinants, which is this part of this simple exemplifying graph, and we overlap it with this len2 state, phi 1 dagger, phi 1 dagger. This is an example of diagram that you may have. You have a double trace over here and two single traces over here. This I have to be clear. What the effective theory computes is the unintegrated diagram. That is to say, this integrand, this product of scalar propagators in this case, with the correct powers of the couplings, of course. And this is a sketch that I took from the Mathematica code, where you also have an idea of the topology of the diagram in X space. So it is up to you then to manipulate this integral. You can do maybe Bethe-Salpeter summation of the diagrams, where you don't need some explicit regularization scheme, or you can just do perturbation theory. This is up to you to decide. Equipped with this tool, I want to proceed to some parts that are more interesting maybe from the physical point of view. That is to analyze some correlators with this tool. The study for now is limited to the biscalar fishnet, precisely for the diagrammatical complications that these operators present, and also for our current implementation of the calculator. Still, it is challenging, and all the challenges in ultimate analysis come from the breaking of the R symmetry SO6 down to U1 cross U1. The downsides are essentially two. Since we don't have SO6 anymore, there are operators that used to be related by SO6, but now since this is not a symmetry anymore, they won't be related by symmetries, so they will behave distinctly, quantum mechanically. So you have to consider the correlators separately. This creates a zoology of potentially of correlators. So you have to make some wise choice in order to keep the survey conservative. We still can keep this condition, although since we don't have the supersymmetry, we don't really mind relaxing this constraint if possible. The second drawback is the loss of supersymmetry. This creates many extra challenges because determinants are no longer protected. On general grounds, you can think that may acquire anomalous dimensions. This is in total analogy to the BMN vacuum, which is no longer a vacuum state. It has anomalous dimension in the fishnet. And about their correlators, while 2 and 3 point functions of BPS operators we know very well, they're protected. Now already the problem of 2 point functions potentially can become extremely cumbersome. So if you were to proceed perturbatively, what you would do, also in the literature of fishnet for some single traces, what you would do would be to compute the 2 point functions, extract the missing metrics, so filling all the entries, all the possible transitions, and then diagonalize it, or better, to decompose it into Jordan blocks. This is a logarithmic CFT. Now the procedure for these determinants is complicated by the extent of the potential operator mixing. They potentially mix with other operators that are spinless, same bare dimension and are charges. These operators, if you don't have a guideline, they can come in a very large number. It is difficult to get an handle on them, unlike some examples done in the fishnet for short operators. And there is also technical limitation, because speak about 2 point functions, we cannot, with the current technology, handle transitions from determinants to other sort of operators that are not determinants. So the spectral problem certainly requires a lot of attention, a lot of insight. We didn't go too much deep into that, although we make some considerations and we argue some considerations in the paper. But it's still fairly honestly beyond our control. Certainly this is a pressing issue that would require more study ahead. I want instead to say from a qualitative point of view, how we can assemble 3 and 4 point functions, leaving aside these problems of discussing anomalous dimensions, identifying primaries. Okay, let me sketch some pictures. We have a bunch more in the paper. To keep the survey very simple, we took always a pair of determinants or determinant-like operators, and we always added a single trace. Single trace that can be of length 2 or greater than 2. These cases must be considered separately for the diagrammatical properties. There are cases that are non-trivial, but go back to cases that have already been studied in the traditional literature. If you insert an insertion each, phi 2 and phi 2, in this pair will effectively contribute with a len 2 of this sort, phi 2 trace phi 2. This is a bilocal operator of minimal length. And due to asymmetry, so R charge considerations, you can, for instance, overlap it with this phi2 dagger, phi2 dagger. This goes back to a case that was analyzed in the literature. I don't want to say too much about that. It was the simplest 4-point function that was exactly solved and resummed using Bethe-Salpeter equation. It was written explicitly as an analytical function of the couplings. There are cases that are less trivial, brings more complication in the game, like adding instead phi1 and phi1 instead. So you can certainly have a class of diagrams where the pair of determinants will contribute this length 2 effective state. And this will go all the way down to get contracted with this phi1 dagger, if we insert this as a third state. And this is precisely the same class of diagrams that also enter here. But we have a huge variety. We have a second class where now this pair will contribute with the length 4. This is exactly what I was saying at the beginning. It is not set in stone that whenever you have, for instance, a length 2 on the other side of the chain, this will can only overlap with a length 2. You can have a variety of operators that can overlap with this and create very complicated graph structures. I can make more considerations on these diagrams, but I prefer to make, they would hold the same on this. I want to say the same, having a look at more complicated operators. Now considering operators of length greater than 2, like these multi-magnon chiral states. You can prepare these states, phi2 dagger and phi2 dagger. These are pure determinant. And then insert very carefully insertions. And again, if you're not careful, the diagrams tend to have a complexity that goes beyond control. So you have to be careful, for instance, adding phi1 dagger in number L divided by 2. These are the diagrams that come out of this 3-point function. So I spread out around the circle here the contribution that stems from the determinant pair. And in the middle, I place the multi-magnon state. So all around here, what is the state that will contribute? Well, for planarity, since it has to contract a single trace, for planarity, I will have a length L, or in this case, a length 6 intermediate state. And not only that, since there is this strange alternation between phi1 dagger, phi2 dagger in x1, x2, all around here. We made this observation in the very first picture when we were describing diagrams. So since we have this alternating boundary of this lattice, this will enforce some conditions on O in order to have a tree level. That is to say that the phi1 and the phi2s must alternate. This is an example of T-level diagrams. Of course, this can renormalize, and you can have the usual spiral graphs of the traditional literature. But again, with some differences that would make these computations, I think, challenging, certainly different from those seen in the spectrum of the fishnet, where the same diagrams topologically they appear, precisely due to this boundary, which is alternating. These propagators do not end on the same point at infinity. This is not a 2-point function, but instead they have this strange alternating pattern. And of course, I remind you, this is a non-trivial observation, that if you were to proceed perturbatively, remember that you're not interested in computing divergent parts of these diagrams. You're interested in, for instance, computing the renormalized finite structure constant perturbatively. So some operations that are performed on these spiral graphs in the traditional literature, they cannot be immediately applied anymore so straight away. For instance, amputating the outer propagators, because this will likely change the finite parts. So if you were to proceed to compute these correlators, you would need to be very careful and to generalize the current techniques that we have, despite the fact that, of course, it is the same kind of planar diagrams, fishnet diagrams. I probably have a last example before I say something more about works and other future directions, promising directions. This is another example where you can be even more creative and insert insertions in both, again with a wise combination, a wise choice of the numbers. The same, here you have more categories of diagrams. This is one. For the same arguments I said before, you will have a planar a single trace contribution from the pair. And again, this will enforce some R-charge assignments on the scalars. In this case, for instance, it turns out that the phi 2s must be separated by an odd number of the phi 1s. This is again related to this strange condition put on the boundary outside by the heavy operators. The same considerations again would hold also for this, and the same also for the matter of computing these correlators, either perturbatively or with techniques based on integrability. There is, I think, a number of future directions that I want to go through with you in the final minutes. So first, this is a very open survey, and really the first step, what we have seen, of getting an handle on operators that are not single traces, also exploring other operators in gamma deformed and equal for superior mass, in the fishnet limit at least, when they have a large R charge. In this general survey and overview that we started, there are certainly a number of pressing issues. First, the spectral problem. This is interesting because you would, well, from a, say, mathematical point of view, you would be able to quantify these anomalous dimensions maybe exactly as it was done for single traces. But also in the light of some analogy that I made at the beginning, in some sense, extracting anomalous dimensions out of these two-point functions would be equivalent in some sense to measure the mass of baryons from their two-point functions. So maybe you can also think of developing these diagrammatics and enrich it in order to pursue this analogy. Certainly, once this problem is fixed, you can continue exploring the survey and continue studying some particular correlators that are promising than others. Our survey was very broad and general. That was just a selection of the most sensible results. Of course, there's a huge deal of conformal data, also structural constants coming from it. And very likely in this business, you will have to use techniques of resummations. I didn't say a lot about them, but they always involve some effective operator, a graph building operator that applied many times will build the graph for you. And due to the fact that these pairs of determinants, they do not give a state of fixed length, it can be of any length, maybe this will be another direction for studying that many people have taken over the last years to study some particular fishnet integrals. Now the boundary conditions would be different, but maybe some of the same techniques would be applicable as well. There are further directions in integrability to search for integrable boundary states that is so popular nowadays. In a survey by these authors, only giants in n equal 4 seem to be integrable in n equal 4 among a certain class of heavy operators. Although we shouldn't be too pessimistic because we can also throw into the game open strings. Open strings on maximal giants have a dynamics which is integrable, whereas to my knowledge there are some mixed indications about open strings on non-maximal giants. So it would be worthwhile also to have a look at those, maybe in the fishnet. Of course, we can also go beyond the usual fishnets, have a look at BJM, where determinants, subdeterminants seem to be integrable. Maybe there's also in other interesting directions in the fishnet of the BJM, and also in these fishnets of n equal to 2 superconformal field theories in 4 dimensions, where very, very little is known, but it is very interesting from a physical point of view because it cuts out an integrable sector in these superconformal field theories. And maybe this search for integrable states can be very, can bring many results also to in this sector. I finish with holography by saying that a huge important thing in the traditional literature was to explore the large coupling of 4-point functions, because this led to indications that maybe an orographic description that we know by now is the fishnet could have been possible. So maybe with this you would discover some nice semi-classical scaling that would hint at some brain-like description, some sort of expansion of the fish chain. And certainly have a look at something that I said in my introduction about try to reproduce these open strings from the ground up, matching string energies and anomalous dimensions. So this is very rich as a follow-up, and I can stop here with my talk. Thank you very much.
Thank you, Eduardo. Do we have questions?
Very nice talk. And I wanted to ask you if you try to explore some special kinematics for higher point correlators between determinant operators, or rather, if you try to study problems similar to that of higher point 1/2 BPS operators, but instead of trace operators, determinant operators, since in that case we know nice results in the trace case.
Yes, so I must say, I think that all quantitative results are a bit subject to this problem of mixing, to properly identify primaries and also calculating dimensions first before going to higher point functions. So far we didn't do any investigations of this sort, precisely because of this limitation. But it may be possible, maybe you can yeah, we thought a little bit also in the publication that I had in 2021. Maybe there are some cases where you can decompose these determinants onto a set of traces, maybe not just 1 or 2 traces, so they would become some trivial cases, but a set of traces. Maybe there you would have some connections with those results, but that is an avenue to pursue. I cannot say something quantitative, I must say.
Thank you.
I have questions. Fedor has a question.
You mentioned in the beginning some expected relations with separation of variables and with results from our papers.
Yes.
On that. So do you already see any hints of structures of SOV from your calculations that you've done?
No, but you could by, for instance, taking as a starting point 3-point functions involving only 2 heavy states and putting a probe, the local single trace operator. You would be able to do that, and that would be probably a beginning also to see some, even before that, some matrix product structure state. That would be, I think, the next immediate development of this, also the effective theory that I presented. I must say, already building that was very cumbersome and lengthy in time, so we didn't, that would be immediately the next step, anyway, using that, that comment that I made.
More questions? Yeah?
I was wondering, this insertion of one type of fields into the determinant operator, it looks very much like these sure polynomial operators of the South African group. Maybe you could comment on that?
I understood the sure polynomial operators, if you can apply the same techniques you said.
I was asking if it's, in what way is it different, the way that you insert some
yes.
different fields in your determinant operator? It looks very much like the construction of these sure polynomial operators of the South African group.
Yes.
So can't you use some of their exact results, because they have some exact finite n results for these sure polynomial operators? And
you can certainly apply the same logic to those operators, yes, and build a generalization of this effective model. But you said also finite n, I didn't catch.
They have some finite n results. I was just wondering if you're somehow doing something like what they did in practice.
Finite n is something that we don't want to touch in the fishnet. We just want to stay at large n for now. I mean, it all boils down if the fishnet can bring, some more insights, some different results. For instance, exact resummations of diagrams, because this is the whole point in working the fishnet. You have this hope of resumming interacting diagrams. I think that would be the addition, just instead of just repeating a similar calculation, but to see if you can bring new insights from exact resummations of diagrams. That would be, I think, the add-on to bring compared to those studies.
Okay, any other questions? No, if not, let's thank Eduardo again.
Thank you.
And I think there's some local announcements.
Thank you very much. I have just a few things to tell you. First, everybody is welcome, invited for lunch. So you don't have to register immediately before going to lunch, but after lunch, when we will come back, then everybody should register. And also those who would like to come to the dinner then and have to pay, they have to pay in cash. And then we are very sorry for this, but that's how we could arrange it. So let's meet for lunch, like 5 minutes in front of the building. Yeah. I have a few announcements. Yeah. First, most important. Yeah. Kolja, do you have your laptop with you? Because somebody left the laptop in the lunch place. So if it's not you, then we will not tell you. So those who left the laptop can go back and they keep it. Yeah. So the other thing, the poster session is going to be on the first floor. And then I'm sure you find a place, you just go up. And another announcement for the speakers. So for broadcasting, it's much better if you show not with a pointer, but with a mouse. And then you stand there. So for other speakers, keep in your mind. So the afternoon session, the chairman is going to be Ivan. So please start.
So our first speaker is Matthias Wilhelm. He will speak about different aspects of form factors. So please, Matthias.
Thank you very much. And let me start by thanking the organizers for bringing us here together. It's really fantastic to be able to interact in person again after such a long time behind screens. So as mentioned, I'm going to talk about form factors and how we can study them from different perspectives. One is the integrability perspective. This is based on a series of works with Amit Server and Alexander Tumanov, who is somewhere here also in the audience, over there. And another perspective is from a symbol bootstrap, so perturbatively with going to 8-loop orders. And there we also observed a new and quite surprising duality between these form factors and amplitudes. And this is based on work with Lance Dixon, Andrew McLeod, as well as Ömer Gudogan. So let me start with a quick introduction of why we should in general be interested in form factors. Now, one quantity that has been studied intensely in n equals 4, but in fact in any quantum field theory, is the scattering amplitude of elementary particles. It is defined by overlapping the vacuum with an n-particle outgoing state. Now, another quantity that has been much studied in n equals 4, which is important in particular in conformal field theories, is this correlation function of gauge-invariant local composite operators, which we define by taking the product of such operators, OI, at positions xi, and wedging the result between two vacua. This has been studied, of course, from the integrability perspective in the last 2 decades for 2-point functions, 3-point functions, and more recently also 4-point functions. Now, the form factor of such a local composite operator is defined by acting with the operator at position x on the vacuum and overlapping the result with an n-particle outgoing on-shell state. Now, after Fourier transforming the position of the operator to a momentum q, this momentum q does no longer necessarily square to 0 in contrast to the on-shell momenta pi. So in this sense, form factors form a bridge between the purely on-shell scattering amplitudes and the purely off-shell correlation functions. Now, moreover, due to momentum conservation, the n on-shell momenta don't add up to 0, but to the off-shell momentum q, and the operator itself is a color singlet. Thus, the planar form factor has the topology of a cylinder, not of a disk. Now, after this general motivation, let me argue that there's a particular operator whose form factor is especially interesting to study. Now, if you look at the LHC, the dominant production mechanism for Higgs bosons is by fusing 2 gluons from opposite protons in a top quark loop, and in the process also further gluons can be produced. Now, in the physically relevant limit where the top mass is much bigger than the Higgs mass, This amplitude can be described in the framework of effective field theory via the form factor of the trace of the self-dual part of the field strength squared. So this form factor, the form factor of this operator, is what I'm going to talk about during the rest of my talk. And in the maximally supersymmetric Yang-Mills theory, this here is in the same supermultiplet as the famous 20 prime operator, which is another reason why this might be a natural starting point for studying form factors. Already at tree level, this form factor shows some really nice simplicity. It has some MHV scattering formula, which is looking almost identical to the n-gluon scattering amplitude given by the Park-Taylor formula. Moreover, if we are looking at the 3-gluon form factor, there's a certain principle of maximal transcendentality at work. Concretely, it was observed that the two-loop remainder function in planar n equals 4 agrees with the maximally transcendental part of its counterpart in QCD. So in this sense, we can really obtain part of the full answer in QCD by studying n equals 4 super Yang-Mills theory. So next, I'm going to tell you how we can calculate these form factors at any value of the planar coupling in an expansion around the multi-collinear limit. Afterwards, I'm going to tell you how for 3 gluons, so this first part is about n gluons, we can then also bootstrap this quantity perturbatively using the symbol up to 8 loop orders now for generic kinematics, whereas this is for the multi-collinear limit. And finally, I'm going to tell you about this new duality relating this 3-gluon form factor to the 6-gluon amplitude. At the heart of the integrability approach to form factors and amplitudes at finite coupling is the duality between these quantities in Wilson loops. Now, if we have a set of momenta pi, we can define dual coordinates, which already appeared in Florian's talk this morning, by requiring that the difference of xi plus 1 and xi is pi. Now, for amplitudes, here illustrated for the 6-gluon amplitude, we then obtain a Wilson loop with edges pi and corners xi. Now, for amplitudes, the onshore momenta add up to 0. So after n steps, we obtain the same dual point again, which is to say we have a closed null polygonal Wilson loop. For form factors, however, the n onshore momenta add up to the offshore momenta of the Higgs or the operator. So we don't add up at the same position, but at a position shifted by q. And since the conformal symmetry here can, in general, transform also the periodicity constraints, a more dual conformally invariant way to write this is to say that x of I plus n is p of xi. Now, the dual description in terms of Wilson loops comes with a physical picture of some flux tube stretching between two opposite edges of this Wilson loop. Moreover, this was the basis for the pentagon operator product expansion, which describes the closed Wilson loop and thus the amplitude at any 't Hooft coupling in the near collinear limit. Our idea was thus to develop a similar operator product expansion for form factors and equally describe them at any value of the 't Hooft coupling. Now, the starting point is that we decompose this n-sided periodic Wilson loop in terms of number of n-2 pentagons and this two-sided periodic Wilson loop. The idea behind the form factor operator product expansion is that we start now with the vacuum state of the flux tube, which propagates on this top square, and then it experiences a pentagon transition that transitions it to a first excited state, psi1, which propagates on the next square, is experiencing another pentagon transition, and so on until the final state here, the n-2nd state, is absorbed by the two-sided periodic Wilson loop in what we call the form factor transition. Now, this is very analogous to the usual operator product expansion for local composite operators. You can think of the pentagon transitions here as 3-point functions or structure constants, and then the form factor transition would correspond to a 1-point function of the operator in the presence of a defect, something that some of us have also studied using integrability in past years. Now let me give you some more details. These Wilson loops themselves have divergences, concretely UV divergences, associated to the cusps. And these are, of course, dual to the IR divergences on the amplitude or form factor side. Now, one way to obtain a finite quantity is to consider a certain ratio where we take this n-sided periodic Wilson loop and we divide by the two-sided one and the pentagons, and then we have to multiply in again the squares in which these two pairwise overlap. Now, each of these squares is invariant under 3 abelian symmetries, which we can parameterize via taus, sigmas, and phis. And we can moreover then use these to parameterize the geometry of this Wilson loop. So for two squares arising from an overlap of pentagons, we can simply use the same parameterization that was developed for amplitudes. So here, tau, sigma, and phi are just different ways to write the usual dual conformal cross ratios U1, U2, U3. For the lowest square, the one arising from overlapping the pentagon with a two-sided Wilson loop, we can moreover build these two combinations, these two dual conformal cross ratios, using the 3 points here and their periodic images under this operation P. Now, in a conformal frame where P is just a shift, these become perfect squares now. And the third one might expect from amplitudes is actually 0 here. So now we are able to make the main statement of the operator product expansion for form factors, which is that this particular ratio of Wilson loops is given by a sum over all states of this GKP flux tube, and the summand contains a sequence of pentagon transitions and ending in a form factor transition. Moreover, there is an exponent here associated to the propagation on each of the squares, which, in addition to the geometry, contains the flux tube energy, momentum, and angular momentum. Now, these 3 quantities are known at any value of the coupling, thanks to work by Benjamin. And moreover, also the pentagon transitions are known at any value of the coupling. So that only leaves us to determine one building block, namely this form factor transition. And we will also be able to get this at any value of the coupling. Now, this quantity is universal in the sense that it only depends on which operator we are looking at, but not whether we are looking at a 3-point or 300-point form factor. So before going to the details how we can determine this form factor transition, let me briefly recap integrability for the GKP flux tube, or rather begin with the integrability of gauge-invariant local composite operators. Now, as everybody at this conference, or at least most people at this conference, have probably heard of, the problem of determining the spectrum of these gauge-invariant local composite operators, or their scaling dimensions, can be mapped to an integrable spin chain and the spectral problem there. And this can famously be solved via Bethe Ansatz techniques, so we can get these energies at any value of the coupling. Now, what we can also do is include a lot of covariant derivatives between any of these two fields here. And if we are then taking the limit where we take infinitely many covariant derivatives, we get a situation where we have a Wilson line along which these fields or excitations are now inserted at finite differences. Now, in this limit, both the scaling dimension and the twist go to infinity, and the spin go to infinity, but the twist, the difference between the two, stays finite, and we can interpret it as the energy of the flux tube state. Now, for a state with n such excitations, the total energy is simply the sum of the energies of the individual excitations. More generally, such a GKP eigenstate is parameterized by the number of excitations n, their species A, so whether they are fermions or gluons or scalars, and moreover we have their Bethe rapidities. So you can think of the Bethe rapidities as being kind of the momenta of the excitations. Then the form factor transition is defined as the vacuum expectation value of this Wilson loop with a state inserted on this edge, divided by the same Wilson loop without the excitation inserted. Now, from this definition, a couple of non-trivial properties follow that this form factor transition has to satisfy, and indeed we can use these properties, which we call axioms, to bootstrap this missing ingredient, the form factor transition, at finite value of the coupling. The first of these axioms is a property of this two-sided periodic Wilson loop. Namely, it is invariant under rotations along this transverse plane called U1 phi transformations, and it's also invariant under asymmetry rotations. And as a consequence, also the form factor transition has to be a U1 cross SU4 singlet. Now, if we look at the charges of the fundamental excitations of the GKP flux tube here, we see that they are all charged under U1 cross SU4. So as a trivial consequence, the two-sided periodic Wilson loop cannot absorb fundamental single particle excitations. And with a bit more of work, one can show that it can in fact only absorb states that are built from conjugate pairs phi bar summed over I, and similarly fermion antifermion summed over the flavor, as well as the gluon antigluon, here also optionally with some covariant derivatives leading to so-called bound states. And in addition to these pairs, we can also have products of pairs. Now, at the practical level, this means that the form factor transitions are a bit harder to determine than the pentagon transitions, which could really absorb these individual excitations. The remaining axioms 2 to 5 are possible to depict quite easily. The first of them is the Watson axiom, and this is really a property of the GKP states if we exchange two of these excitations, we pay the S matrix. The second property is again a property from this two-sided periodic Wilson loop, and that's a Z2 symmetry. We can just look at it from the other side. That changes the ordering of the excitations and puts a minus sign in front of the rapidities, but doesn't change any of the physics. The third property is related to what happens if the rapidity of the first and the last excitation becomes similar. In position space, this can, for example, happen if the two here become very close to each other at opposite sides of this edge. Now, in this case, they in fact decouple, and we obtain a square transition times a form factor transition of the remaining excitations. The last axiom is called crossing symmetry, and this is telling us that if we are applying two mirror transformations here to the first excitation, we obtain the form factor transition where it is in the last position. And recall that the mirror symmetry here sends the energy to I times the momentum and vice versa. Now, from this, we can find a simple solution at finite coupling for the pair of fermion-antifermion and the gluon-antigluon pair with the also bound states here included. And this simple solution is just given by the inverse measure times a delta function in the rapidities. So the inverse measure is forced on us essentially via the square limit here. It's the square transition. Now, for the scalars, we weren't able to immediately write down as simple as this a solution. So what we did instead was to solve these axioms order by order at weak coupling. And there we also enjoyed a fruitful interplay between the integrability-based description and this symbol bootstrap, which I'm going to talk about next. The founding principle behind this interplay is that the loop expansion of these two sides doesn't really line up perfectly. Instead, if we have the result for the form factor transition on one side at a given loop order, this allows us to reach the next loop order at the symbol bootstrap, which then in turn allows us to reach the next loop order for the form factor transition, a bit like these funny ladders with alternating smokes. So playing this game for a couple of rounds, we were able to guess now the finite coupling description also for the form factor transition. And here recall that the pentagon transition for two conjugate scalars is given by a tree-level value, that's a ratio of gamma functions, times exponential of some source terms that are evolved with the BES kernel. Now, what we found for the form factor transition was a similar expression with a tree-level value given by a ratio of gamma functions, but now the source terms in the exponential are really evolved within octagon kernel. Now, the 1,1 element of the octagon kernel, the octagon anomalous dimension, occurs, of course, for the octagon, which gives its name, but also for the origin of the 6-point amplitude. Now, at this moment, we don't know really why this kernel occurs in these different contexts. Maybe there's something deeper about it, but maybe it's just n equals 4 super Yang-Mills theory being lazy. Now, using this solution, we find a perfect match with a perturbative data up to 8 loop order, but also with a minimal coupling solution to the axioms at strong coupling. So far, I talked about the 2-particle form factor transitions. Now let's go to 2n particles. As we already heard previously, an important property of integrability is factorized scattering. So for example, the spin chain 3-to-3 scattering matrix is given by a product of the spin chain 2-to-2 scattering matrices. In a similar way, also the pentagon transition for n particles can be factored. And we also found that the form factor transitions for 2n particles can be built from a factorized ansatz. For example, if we have the form factor transition of gluon, fermion, antifermion, and antigluon, this is just the product of the one for the fermion, antifermion, and gluon, antigluon. Now, we have worked these out explicitly for everything involving just 4 excitations. For a higher number of excitations, there's still a matrix part that's independent of the coupling, though, to be worked out. Now let me switch gears and tell you about the simple bootstrap, where we are able to now determine the 3-gluon form factor for general kinematics up to 8 loop orders. And if you got lost in the previous part, now is also a good part to rejoin. So to do this, we need to have a bit of an understanding of what functions occur in quantum field theory. And at 1 loop order, these are polylogarithms. So for example, in 2 dimensions, the 1 loop bubble evaluates to a logarithm, and the 1 loop box integral in 4 dimensions evaluates to sum of dialogues in the product of logs. Recall that this classical polylogarithm is defined recursively by integrating the one of weight n-1 with this simple integration kernel dt divided by t. And then this recursion starts with the monolog, which is just minus the logarithm of 1 minus the argument. Now, more generally, we also have these multiple polylogarithms occur, where in addition to this kernel dt divided by t and the kernel dt divided by 1 minus t, we also have these general kernels dt divided by t minus a occur. Now, as Florian has already told us earlier today, quantum field theory does not stop at these functions, but there's infinitely many more classes of functions which also involve elliptic curves or integrals over Calabi-Yau manifolds. And if you go to 4 dimensions, then this is a Calabi-Yau L-1 fold. So there's a slight difference to the first talk due to the different dimension. And this is really a full scattering amplitude, the only contribution to a particular component scattering amplitude in n equals 4 or in the fishnet theory. So it also occurs in n equals 4. We just don't see it if we're naively looking at the pentagon OPE, because that is a sum representation. For the purpose of this talk, the multiple polylogarithms will suffice, though. They are also called Gonchow polylogarithms and first occurred prominently in the n equals 4 or scattering amplitudes literature in this 2-loop 6-gluon remainder function. And the remainder function is just the alternative finite part of the amplitude, alternative to this ratio of Wilson loops mentioned earlier. Now, the result that was found for this quantity fills 18 pages. And if you have very, very good eyes, you can see that it's written in terms of individual Gonchov polylogarithms. Now, when Spradlin, Vergu, and Wolowitz saw this result, they asked Gonchov what to make out of it. And Gonchov taught them a trick by which these 18 pages can be actually written in just 2 lines. And if I were to give the definitions for this L4 and the J here, that would just add 2 more lines. The trick that Gonchov told them is called the symbol, and it is defined via the total derivative. So the total derivative of such a Gonchov polylogarithm of weight n can be expressed as a sum of Gonchov polylogarithms of weight n minus 1 times d log of phi I, where phi I is now a rational or more generally algebraic functions of the momenta. Then the symbol of this function is recursively defined as a sum of the symbol of these lower weight functions tensor a logarithm. Now, to give you an example, we can look at the dilogarithm. Its total derivative is just minus the logarithm of 1 minus x times the d log of x. So the symbol of this function is just minus the logarithm of 1 minus x tensor log of x. Now the symbol itself here is a tensor product, so it's multilinear and thus easy to manipulate. Moreover, the entries of this tensor product are logarithms which satisfy log a, b equals log a plus log b. So that makes the symbol and via it the multiple polylogarithms easy to manipulate and very well understood. If you want, the idea is to decompose these complicated functions into simple functions in the same way that we can decompose a Lego model in terms of individual building blocks. Amazingly, this idea can also be reversed, and we can use these simple functions to build complicated functions. And this goes under the name of bootstrap or symbol bootstrap. The idea is to make an Ansatz for the result in terms of polylogarithms via the symbol, and then to fix the coefficients in this Ansatz via physical constraints. And this way, it's possible to avoid Feynman diagrams and Feynman integrals altogether. Let's look at the example of the 3-gluon form factor. So here, looking at the 2-loop result, we see that the building blocks, these log of phi I, are now given by log of ui or log of 1 minus ui, where u1 is just S12, the Mandelstam variable, divided by q, the momentum of the operator or Higgs squared. And via momentum conservation, these 3 add up to 1, so only 2 of them are linear independent in the same way that phi was 0 in the Wilson loop. Now, for the Wilson loop, we used this ratio of Wilson loops W3 to obtain a finite quantity. Here, it's advantageous to use a slightly different normalization, the so-called BDS-like normalization, because this one here breaks cyclic invariance, and we can restore the cyclic invariance if we multiply by the exponential of the cusp on normalized dimension times this product of logarithms. Now the starting point is a tensor product at L loops in these 6 letters of length 2L. So if you approach it naively, this is a 6 to the 2L dimensional vector space. So you have to do just linear algebra to fix the coefficients. And the way we are doing this is by imposing physical constraints. And the first one is essentially Bose symmetry. this 3-gluon form factor is invariant under any permutation of the 3 gluons, and thus also of these 3 combinations of their momenta. The second requirement is a purely mathematical one. We know that partial derivatives commute, and the symbol is defined via the total derivative, but this is not necessarily a property of everything in this tensor product, so there's some non-trivial constraint coming for something to be actually the symbol of a function. The third constraint is physical again, and it is that the branch cuts of the form factor have to start at Sij equals 0, which is the threshold for particle production in a massless theory. Now, if we look at the letters here, this one has indeed a branch cut for the argument being 0, as we know from the logarithm. But here, this one would also have something for this being 1, which it shouldn't. So only log of ui can occur in the first slot of this tensor product, not log 1 minus ui. Similarly, we also observe, looking at the 2-loop data, that the last entry can only consist of these 3 linear combinations of the total 6 entries. And then if we further look at the data, we find more and more such constraints at 1 loop order, which we then impose at the next loop order. Finally, via integrability, we know, of course, the near collinear limit, which imposes more and more, in fact, infinitely many constraints that allow us to single out a unique solution and impose, still using the remaining constraints, infinitely many cross-checks on it. And this way, we have found new results at 3, 4, 5, 6, 7, and 8 loop order, which is a new record for this bootstrap. Now, in particular, this is really expected to give a part of the result for Higgs physics at the LHC. Now, before concluding, let me also mention this new duality, which is, to be 100% concrete, between the cosmically and BDS normalized quantities for the 3-gluon MHV form factor and the 6-gluon amplitude. So concretely, we can obtain this 3-gluon form factor if we take the 6-gluon amplitude and we replace the dual conformal cross ratios here by simple functions of the form factor kinematics, and moreover we apply this antipode map, which is part of the Hopf algebra structure of multiple polylogarithms. At the symbol level, the antipode map just reverses the order of these letters of the entries in this tensor product. However, the antipode is also defined at the level of functions and also for numbers, but they are modulo I pi. Now, something really strange about this duality is that it relates completely different physical properties on the two sides. For example, the first entry encodes the discontinuities of one side, and via the reversal of the order with the antipode, this is related to the last entry, which is encoding the derivatives. Also, through this duality between Wilson loops and form factors and amplitudes, this antipodal duality also implies some duality between the periodic and closed Wilson loops. Now, we've checked this duality up to 7 loops, so it's true beyond a doubt, but we still have no physical motivation of why it should even exist. Now let me conclude. In this talk, I've told you about the operator product expansion for form factors based on the dual periodic Wilson loops, which allowed us to determine these form factors in a near collinear expansion at any value of the coupling by bootstrapping the one missing building block, this form factor transition. At the same time, this allowed us also to bootstrap via the symbol now at general kinematics, but perturbatively up to 8 loop order, the 3-gluon form factor. And this is in particular expected to give part of the full result for Higgs physics at the LHC. Moreover, we observed a surprising duality between the 3-gluon form factor and the 6-gluon amplitude here, which is quite mysterious. These form factor transitions, which we bootstrapped, still have one detail to be worked out, namely this coupling-independent matrix part, which would be interesting to work on in the future. And so far, I've only talked about MHV, but I'm happy to report that since last week, actually, also NMHV works. And here we also looked only at the simplest operator, this self-dual part of the field strength squared, which is also in the same supermultiplet as the 20 prime. But it would also be interesting to look at further operators, both from the integrability as well as from the bootstrap perspective. Finally, it would be very interesting to find a mathematical or physical derivation of this new antipodal duality, as well as a generalization of it, which is something else we're currently working on. At this point, let me stop and thank you very much for your attention.
Thank you, Matthias, for the nice talk. So are there any questions?
Hello? Hello? So when you said there is a duality between the 3-gluon form factor and 6-gluon amplitude, is it, I guess, for some particular operator, or how general that is? And if you change the operator, how much will it change and so on?
That's a very good question. So what we looked here was really this operator, which is the 20 prime, or the one that's really relevant for the Higgs amplitude. But it would be interesting to see whether there's a similar duality also for other operators. But then we would first need to work this out.
This antipodal duality is not just due to the fact that you've got the same variables in the game and then somehow the space of functions is simply restricted to be what it is?
Could you repeat the question?
Okay, I was maybe too far away. So this antipodal duality is to a good extent probably related to the fact that you have got the same variables more or less. No, there are 3 cross ratios in this amplitude, and there are how many variables on?
There's 2 variables for the form factor. So if you are making this replacement here, this is actually bringing you to a 2-dimensional subspace. So this is the subspace, if you know these variables, related to delta equals 0. So usually also the alphabet here has 9 letters. Here it has 6 letters. And if you know the notation, these biletters, these odd letters, they vanish under this replacement. So here you're really on the parity even subspace.
Right, so if the amplitude classification of the functions is unique in some sense, I mean, can you find something else under this identification?
Sorry,
Can you find something else if the amplitude space of functions is unique? I mean, as an explanation for the antipodal duality, is it not just that you're forced to fall on the same things?
So I find it hard to understand you. So the question is whether there's a unique solution on this side or this side, or?
Well, I mean, in the amplitudes, you pretty much know from the work of Dix and Drummond and whoever else, so George was in that and whoever contributed, what the functions are.
Yes,
so
exactly.
as long as you can identify, like, could you have found something else for the form factor?
So a different duality. I mean, if you have a good suspicion, then of course you can look for something. But this match here is highly non-trivial. And if you look at our 8-loop results here, this has 1.8 billion terms, and the coefficients of all terms match. This one is only known up to 7 loops, so it's slightly less than a billion terms at 7 loops, but it's highly non-trivial that this works even at the level of the symbol. And then it works also for numbers. If you go to particular limits, you have got multiple zeta values, so it also works there. So if you have a good guess, then there's plenty of data to check whether it works. But yeah, we're currently trying to go to more gluons, and I guess we don't have a good guess there yet.
Right, okay, thanks. I mean, so there's plenty of space to get wrong. One other thing. You say this is what you need for the LHC, but this is an n=4 calculation, I understand, though. It's a
Yeah, so usually you don't have this principle of maximal transcendentality for amplitudes in n=4, but this was this amazing result that the Queen Mary group found that for this particular operator, there was the QCD calculation done, and the n=4 calculation then done by these three. And they found that really this maximal transcendental part agrees. So this is the leading order in this particular limit, but also for the subleading order, interestingly, the two theories give the same piece at maximal transcendentality.
Okay, thank you very much.
Thank you.
I have a question. So, very nice talk. I was wondering, regarding this antipodal map, is it something you can formulate at the level of the OP, in the collinear limit? Or?
Yeah, that's a very good question, and I think it boils down to the fact that we are really using this antipodal duality, which is at the level of multiple polylogarithms. So it's manifest at the symbol, but then if it's actually about numerics, it works only mod I pi so far. So if you were able to see the symbol of the OPE and ignore I pi, then this would be possible, but I don't know of a way. Similarly, for both quantities, there's a strong coupling description in terms of volume of this minimal surface, but currently we have no notion of what this volume mod I pi should be. So until we fix this I pi, if it's at all possible to fix it, we cannot make any numeric or OPE or minimal surface statements.
Okay, thank you.
Thank you. Very nice talk. I have 2 questions.
Thank you.
One, why did you stop at 8 loops? Could you not do better? The computer was not big enough, or there's other?
So 9 loops is currently running on the cluster. So the thing is, integration is hard, and we are able, with this bootstrap, to reduce integration to linear algebra. But if your matrices are sufficiently big, Okay, you can play some tricks like finite fields, which is what you're doing, but still at some point even linear algebra crashes your kernel and requires you to go to a cluster with a lot of RAM.
I see. Second question is, this antipodal map has some like physical intuition for it? So you're changing the first and the last letter. Can I understand this is some amplitude is some weird limit or some different, like, I'm looking different.
I'd love to learn about any physical intuition behind this. So, I mean, it's a limit in the sense of, I mean, you're going to the parity even subspace, or you could say it's a like twisted forward limit, where now for the 6 momenta, the 4th momenta is minus the first one, the 5th is minus the second one, and so on. But I mean, all of this could be red herrings until we are able to find the second example of this duality. And we're working on that, but yeah, it's a work in progress.
Thank you.
So it seems that there are no more questions. No? Okay, let's thank again to Matthias for this very nice talk.
Thank you.
Test. Our next speaker is Enrico Olivucci, who will speak about Todd Bootstrap, new polygons.
Okay, so good afternoon to everybody, and I'm really glad to be here, back in person in IGST. And I want to thank a lot the organizers for inviting me to give a talk in here. So today, in fact, I will speak about some results related to higher point correlators in gauge conformal field theory. And the plan of my talk will be structured as follows. So I will give an introduction with some motivations, and I will point out which objects do we deal with. Then I will explain in which particular kinematic conditions do we work and what effect we expect and in fact observe about higher point correlators. And finally, I will explain our result. What is our result, which is a conjecture for some objects I will call null polygons. Finally, if there is some time left over, and I will put a timer, in fact, I will be able to provide you some not so technical detail and answer or formulate myself, in fact, some questions. So we deal with the n=4 theory, which is conformal gauge supersymmetric field theory, and we will restrict ourselves in this work in the large unlimit, therefore with planar correlators. In fact, we not only consider planar correlators, but planar correlators of very simple operators, which are, oh, here there is a square missing, of course, second power, which are operator of, I'll consider them to be operator of 2 scalar fields. You know very well n=4 has 6 scalar fields which are distinguished by an index I, and those fields are contracted with a null tensor, a null vector y, which means such an operator will be a symmetric traceless tensor. Okay, but this property of being a symmetric traceless tensor with respect to the R symmetry SO6 or SU4 if you prefer, is such that due to supersymmetry, this operator do not get corrections to their scaling dimension. And therefore, say the object of our general research is to study endpoint functions, that is, in the planar limit insertion, if you want, on a sphere of n BPS, one-half BPS operators, each standing at a certain position in the space-time X, and being characterized by a certain polarization vector Y, which determines which component in this six-fold vector are selected. Okay? In fact, these one-half BPS operators are very simple, not only because they are protected in the scaling dimension, but also in the 3-point function. Nevertheless, their 4-point function is not trivial. Okay? And it is a very interesting object for the following reason. Because we have OPE. Therefore, we can use a 4-point function of operator which are very boring in a sense to extract information, very non-trivial informations about operators which have correction in a scaling dimension and are even spinning. Simply, if I consider the operator product expansion, when the position of the operator O1 gets closer to that of the operator of 4, and similarly, or equivalently, I should say, 2 and 3, well, we know that I can expand this 4-point function in a certain function fixed by symmetry, the conformal block, and which are multiplied by certain 3-point structure constants, which are the 3-point structure constant of the two external operator and a certain primary operator of dimension delta and spin S. Okay? So 4-point functions are, in a sense, a tool to extract information about 3-point functions. Okay? So in fact, if we stick to one-half BPS operator, we can still study not only structure constants of 2 BPS operators and a non-protected spinning operator, but we can do better, right? Because if you consider higher point function, and that's why higher point function, in my point of view, in our point of view, are a very interesting problem to study, despite the fact that in a conformal field theory, 2 and 3-point function, in a sense, capture the content of the theory, is that because they are sources, they are, if you want, machines that produce a lot of non-trivial conformal data. And you can think about this along the lines of the work of multiple groups that I reported here, and I'm sorry if I'm forgetting anybody. So you can take, for example, multiple OPEs, such that in the operator product expansion that produces, that is expressed via a sum over non-protected and spinning primaries. So these spinning and non-protected primaries, they can OPEd, they can put close to other operators, being their external or being their the result of another OPE, and getting in this way structure constant, therefore 3-point function in the theory that involve less trivial operator, a more complicated operator rather than one-half BPS. Okay? This is the pictorial example I'm giving is a particular channel, so a particular way of taking these limits, but it's not the only one. And in fact, not being the only one, it allows to do some bootstrap. Okay? So now I want to, after giving this motivation, which is, I think, a very good motivation to learn something about higher point correlators in the theory, I want to show what is the type of object we deal with and in which situation can they appear. And those objects are the disk correlators. Right, so if I consider a planar theory, generally speaking, I will be able to see that all the Feynman integrals entering the perturbative expansion of the correlator can be drawn, in fact, on a sphere, okay, on a surface of gene 0. But there are certain limits, certain conditions under which the sphere is factorized into the product of two disks. And these are the kind of correlator I want, the kind of situation I want to study. So if I consider just a 4-point function so far, and I consider 3-level graphs that describes this 4-point function on the sphere, well, you can see that these are given by product of propagators that here I draw using these black lines connecting red dots. And if the correlator is planar, you see there are only two possible choices for the most general skeleton tree-level diagram, which are what I'm drawing here. There is nothing more. If I want to have something more complicated, I must, if I don't want to cross the lines, add genus to the surface, right? So go to non-planar suppressed corrections. Okay. Now, so here I'm just reporting the notation I'm using, and so in fact the general tree-level scalar, the general tree-level skeleton diagram is, after all, characterized by the number of propagators that extend between each couple of points. And the propagator stripped of constants is basically this type of object. I'm considering scalar fields. This is bare propagator. I have a numerator given by the scalar product of these polarization vectors and a certain denominator. Okay? So in perturbation theory, in order to understand now under which condition this sphere factorizes into two disks, you can consider perturbation theory and see how to perform the perturbation theory of a certain skeleton diagram, so of a certain contribution in the correlator. Well, as usual, just if you want by Lagrangian insertion method, or simply, every time I add a certain power of the coupling, I will also add a certain, add one vertex. Okay, one interaction vertex inside the graph that will contract with the fields and will be integrated, and so on and so forth. So, in fact, from this point of view, you can distinguish clearly two situations. If I consider, again, 4 points, here I'm explicitly drawing more propagators. Okay, so for example, this hashtag here will be 3, or on the other side will be 3 as well, but it's very generic. Illustrative picture. The difference between what I have on the left and what I have on the right is that what is on the left are vertices that are inside the square, while they could be outside the square, right? Because I am on the sphere. Well, everything which is outside of the square is on a disk. Everything which is inside the square is on another disk, and the two disks are glued along the square contour. While what is on the right, you see it couples the inside and the outside of the square, because you have some vertices which pass across this bundle of propagators in the square frame. Okay? So it is clear that this type of contribution, this type of correction in the perturbative expansion can happen only at a certain, they can start only at a certain loop order. Right? Because they should traverse all these propagators. So there is a minimal number of vertices that you need in order to have such terms. And the idea that was used, for example, by Frank Coronado in his study of the octagon was to push this number of propagators along the bundle to infinity, and in this way somehow to decouple the inside and the outside of the sphere into two disks. This is, in fact, very inspiring for our work, and in the end, I will show this concept will come back, or rather, I should say, this framework will come back in our investigation, but it is not what we did. Okay? So the general picture, this general picture I'm proposing can be achieved actually not in this not acting on the large charge or the large dimension of these 1/2 BPS operators, but rather using a particular kinematical setup. Okay? So what I want to achieve is, in general, right, this factorization of a certain sphere with the various correction into the product of two objects which are in a sense independent, so they are completely factorized, and you can see the inside of the disk being the first object, the outside of the disk being exactly the second object, okay? With its perturbative correction, which can happen only inside or outside of the square contour. Okay? And this other framework in which this decouple happening is a specific double scaling Light-Cone limit for the propagator, for the correlator, sorry. Once again, here I'm still restricted to 4-point functions, but I later generalize this to higher points. So what does it mean? I want to consider 4 points, these 4 points that are connected by propagators, to lie on a null contour. So every edge of this square to be in fact null. And we know that besides, of course, the power law divergence that stands in front of the correlator, so the leading, this leading singularity, then there are also, in presence of quantum correction, logarithmic divergences on the top of that, because, well, you know from the structure of the conformal block in an OPE, for example, that there is a part containing log z bar, and if I consider 3 points on a line, which I can always do in a conformal theory, 0, 1, infinity, and the third point, here should be z and z bar, somehow the bar was cut, I'm sorry, but this 4th point is on the plane. If I consider the OPE, which I presented before, okay, the conformal block as I can factor out the singular part of the conformal block when z goes to 0. Okay? Setting z to 0 means setting these two distances, which are dashed, to be null, to be on the light cone, and therefore producing log divergences from this exponent. Okay? But taking this limit, which gives indeed infinite quantity, forced to restrict to some finite quantity, which we define via double scaling, which extract the so-called leading logarithm, so the leading logarithmic divergences. Sending the coupling G to 0 and the edges to be null, but setting G square log Z to be finite, well, one discovers that the only corrections, the only coupling-dependent corrections to this 4-point function are in fact encoded in the one-loop anomalous dimension coming from this exponent in the conformal block expansion. Okay? While this second function is regular when z goes to 0. Okay? Then we want to do more because we want all the contour, as I was mentioning, all the square to be made of null edges. So a second limit can be taken, that is z bar going to infinity. When z bar going to infinity, well, also this function f will contribute with some divergence. And in fact, the real double scaling limit we will consider is not just g square log z, which would be the leading logs in the light cone OPE, but it is g square log z bar to be finite. Okay, and so we can define a variable s. Here I report s to the 2n, and it is an observation that at n loops, that is at order g to the 2n, you can have maximally log n to the z and log n to the z bar. Okay, and so this is the new variable. So if you can compute a 4-point function of 1 BPS operators in this double scaling limit at every value, at every loop, at every power of g, but in this double scaling limit, which means at every power of s, then you have a no-loop result, which from the point of view of the dynamic of the quantum corrections to the 2-point functions depends only on the one-loop dilation operator of the exchanged operator, right? Because it depends only on gamma 1. And this is the limit we are interested in. This result is known. This result is known, and I invite you to consider this picture of the skeleton diagram and imagine that this is not just this 3-level diagram, but you can consider all the corrections that you would get in the perturbative expansion. And therefore, in the double scaling limit, you get a function of this variable s I just defined. And this object indeed shows this factorization that is expected into two functions, depending, as you can see, only on the number of propagators connecting point 1 and 3, the first function, O with L, and the number n of propagators connecting 2 and 4, the second function, O n. So these are exactly the same class of functions, but they are distinguished by these indices L and n. Okay? This is pretty remarkable. It does not depend on how many propagators connect 1 with 2, 2 with 3, and so on. So it does not depend on which 1/2 BPS operator we are considering, how heavy those objects are. Okay? You can consider, of course, 20 prime, for example. Well, in that case, you will not have enough propagators to have any L or any N, but you can consider 3, 4, 6 length operator, and the story will be the same. Right? So this object is computed, in fact, and its computation is based, in a sense, of on some integrability technique, which I cannot explain here, but take it as a known result and observe it that it is given by a part which you could call Sudakov factory if you want, but it is this exponential of minus s squared, okay? And then another function which depends on how many of these propagators, diagonal, non-light-like propagators, are in the corresponding skeleton diagram, and this function is in fact also known at exactly. In fact, it is a solution of a well-known integrable hierarchy, the so-called Todd equation. This Todd equation, in fact, can be solved non-perturbatively exactly, and it takes the form of a determinant of modified Bessel function. So you have a matrix of size n, where n is the number of this diagonal propagator, which from now on I will call bridges. And it is an n times m determinant of modified Bessel functions. But in fact, even if you didn't know the integrability story that gives you this determinant, you can still observe that the equation is homogeneous on the left. It is not the case on the right. And so given some initial boundary condition, you can solve iteratively this equation to the order you want. Now, in fact, this result I presented so far is not our result. It's a result by Andrei Belitsky and Grisha Korchemsky. Therefore, what we want to do is consider higher point functions. And a suggestion in this sense comes from the fact that, from an observation, that if you take 1/2 VPS, or maybe I should say short, or not only 1/2 VPS, in fact, originally, but say short operators like 20 prime operators, if we look at 1/2 VPS, but also Konishi. Okay, yeah, if you take endpoint function of, say, 20 prime operators, and you consider this limit IM focused, edges along the polygonal contour to become light-like, there is a correspondence between the correlator, so the correlation function, and Wilson loop in the n equal to 4 theory. Wilson loop on the polygonal null contour. Okay, and this correspondence was pointed out in the literature, and it was also by Aldai Korchensky, Eden, Maldacena, Sakachev, but it was also used much more recently in order to bootstrap, in some bootstrap paper about correlators of 20 prime operators, of 5 or 6 20 prime operators, where you can really see in practice how the result contains the information about, is based on the information of the Wilson loop. Well, this correspondence is suggestive because the Wilson loop in this limit enjoys this factorization where the adjoint Wilson loop gets factorized in the product of two fundamentals, and therefore makes us think that this factorization of a sphere into disks should hold also for higher point function, and not only for 20 prime operators, but also for any 1/2 VPS operator. Therefore, also in that situation where you have these bridges, where you have not only a counter in the skeleton tree-level diagram, but also some diagonal propagators, which will give a very non-trivial and interesting structure. So let's focus on this type of object, and these are what we worked on. And consider 20 prime correlator in double scaling limit of n 20 prime operators. One know from this correspondence, taking the double scaling limit I have described, that this propagator has precisely this form. Okay, so it's the exponential of minus t1 square, minus t2 square, minus tn square, where ti is a kind of cusp variable. So there is one variable for each cusp of these polygons, that is for any 1/2 VPS operator, defined according to this double scaling limit. Okay, so g squared times the logarithm of the distance to the left of the point I times the logarithm of the distance to the right of the point I. This comes from the correspondence, but we want to consider indeed more involved situation. Okay? In a sense, if you consider the same prescription on 4 points, you would have only e to the minus s squared. We want to understand what would replace for a higher point this solution of the Toda equation, this nice determinant. Okay? Okay, this is really the same. So what about the pentagons? Okay. Now consider a 5-point function and consider a 3-level diagram. Okay. 3-level diagram, the most general 3-level diagram you can consider without crossing lines, so in order to be planar, is the following. Okay. So you have 2 points that can emit 2 propagators that don't stay on the light cone contour, one inside emitting h and k, and one outside emitting h prime and k prime propagators. It's obvious that you cannot have no other 3-level contribution is possible if you want to be in the planar limit, right? This is the most non-trivial, the richer one. Okay? And so the claim, the conjecture, our conjecture is that if you consider this object and you send indeed this light blue contour to be on the light cone, this contribution, and with all its perturbative corrections, factorizes into 2 functions, which I will call P here as pentagon. Each function depends only on h and k and h prime and k prime respectively, so only on the number of propagator of the original skeleton, of the original 3-level contribution, and is completely insensitive of respect to the other, therefore inside and outside of the pentagon the couple, the 2 disks the couple, and those are function of these double scaled t variables, each for every cusp. Okay, this is a conjecture, but what are these functions? Okay. We know what are these functions. We can conjecture also what really these functions are. Okay, so once again I have this exponential factor, which one could guess from the knowledge of Wilson loop and the correspondence with the 20 primes. But in presence of non-zero h and k, I will have also a non-trivial function phk. And what we find perturbatively, and therefore we do conjecture non-perturbatively, is that this function p also solves a system of Toda equations, but actually a system of 2 Toda equations, which are more complicated each respect to what is in the case of the square, because are 2-dimensional Toda equation, or even called Toda field theory. And maybe you don't recognize them. If you don't recognize them at a glance, is because you can do a change of variable and set them in a more familiar form that you have for the position of sites in a Toda lattice. Okay, these functions have 2 indices, h and k. Therefore, each, I want to explain somehow graphically how do you read these 2 equations if you look at the null pentagon I draw on the right. Okay, so you have one first equation. Okay, you see it contains only 3 variables, t in the differential part, which are 1, 2, and 5. 1 has a special role because it's not extreme of this bridge, of this black bridge. And this, as a Toda equation, it acts only on the first index. You see kappa, index k is always the same, while index h is shifted. And similarly, the second equation deals with the second index k and deals with the second set of 3 variables. Okay? So this is how you read equations if you look at this pentagon. Now, once again, these 2 equations are homogeneous on one side, non-homogeneous on the other side. Therefore, if I supply with certain boundary condition the system of 2 equations, I can solve them at all loops. And in fact, you can guess and check after you develop some experience, of course, it's a matter of guessing, that when you send these 2 special variables 1 and 3 that play this that I depicted with a hat that played a special role in the two equations, because they appear on the right-hand side. If you set them to 0, this object factorizes, and it factorizes in this tau function that appeared as a non-trivial part in the square case. Okay? This tau function, one tau function each for each non-zero cusp, okay? So 2, 4, and 5, and with index the sum, so the total number of propagators emitted by that cusp. Okay? So th plus kappa from 2, th from 5, and t kappa from 4. So now you're ready, after knowing this case, you're ready to guess what is the story for higher polygons that there is for hexagons. So consider a 6-point function, focus on a certain contraction in 3 level, and consider its the perturbative correction to it in this double-scaled null contour limit. So here it is very instructive. I'm not listing hexagons because I could go on forever and I want to occupy time. It is just because it's the first time you get more than one possibility how to dispose the bridges. So these lines, these black lines inside the polygon. Before, they could be only at most in these two directions. Okay? They could be at most 2, and for sure both emitted by the same point. Okay? While here there are 3 possible topologies. Okay? So we distinguish these A and B and C situations, and you can, of course, assume the same conjecture, so having the exponential part, Sudakov term, times a non-trivial function of these t variables. Now, how to fix this non-trivial part? So what are in this case the differential equations, and how to guess or to compute the boundary conditions? Well, let's look at this picture. So we recognize, for example, in picture A, twice the same situation it was in the pentagon. So twice bridges, which I depict with blue, that are that connect next to neighboring points. So for which there is a kind of spectator point, which I depict with a hat. So 1, 2, 6, and 2, 3, 4. And similar in situation B, but differently in situation C, I have 3 of these triangles. Now, in the case of the pentagon, each triangle was associated to a Todd equation, and therefore I can assume the same logic. Okay? So I will have, in the first, for this situation, for this A configuration, there will be 2 Todd equations, but there will be 2 equations that share one point at the level of the differential operator. So in both differential operators of this TODA, there will appear the variable T2. In the second situation, B, this is not the case. There will be 2 decoupled TODA equations. Okay? And in the third situation, there will be 3 coupled TODA equations, as you can read just from the picture. Okay? And in fact, what will be the boundary condition now in order to fix the solution of the system of TODAs? And in particular, this tells you where do M, these red bridges of index M, enter in case A and B, because they don't contribute to TODAs, right? Only bridge L and N are shifted by the corresponding TODA equation. Right? Let me make this point clear, going back to the previous picture. I would like this point to be clear. You see, if my triangle, which is associated to a TODA, has this basis with index H, you see that only H is shifted in the 2D TODA equation. Okay? So similarly, the TODA equations in case A and B shift only L and N, and L and N respectively. Okay? But M, therefore, in this case, will just play some role at the level of the boundary conditions, because I use the same prescription for boundary condition as explained before. So when I set those particular hatted point to have a corresponding t variable to be 0, the result factorizes into tau functions, and this tau function have index, so functions in the 1D TODA hierarchy, with index given by the total number of propagators, bridge propagator emitted by them. Okay. So here, of course, now M enters, and it is it determines the solution. Of course, the type of system of TODA that you would get, coupled, uncoupled, will then eventually show up at the level of the solution in terms of eventual factorization of different part of the polygon, further factorization. But that depends totally on the configuration, right? For example, in case C, all the TODAs are coupled, so there cannot be factorization. In case B, you see that the left and the right part of the hexagon somehow they don't speak to each other, okay? Because there is no equation to couple them, so they will be actually factorized. Okay, so the general conjecture you can do for an n-point 1/2 VPS correlator, if you focus on a certain skeleton, and let me tell you, you can choose at least to 5 points for certain the polarization, the y vector, the polarization vector of your BPS operator. So the precise choice of the BPS operator such that there is only one simple class of these skeletons. So for each of these skeletons, you can, in the null contour limit, assume factorization into 2 polygons, into therefore n-gons in general, which are labeled by the number of bridges, so these propagators that do not lie in light cone direction, and depend on the t variables, 1 for each vertex of the polygon. And we can conjecture at every loop what these objects are, therefore the Sudakov term time a solution of a system of TODA equations. Okay? Once again, you will draw your polygon, you will draw the bridges, and you will observe how many blue triangles there were, and so how many TODA equations, and how many vertex the polygon have, and you will be able to read for every vertex what is its contribution to the boundary condition, depending on how many bridges it emits. Okay. Due to the fact that these TODAs are not homogeneous left and right, you can iteratively solve to any loop and find the solution for the object I started from, that is the endpoint function. Okay? So I would ask how much time is left over?
You started a bit later, so I think you can 4:37. You have 7 minutes more.
Perfect. Okay, since I have 7 minutes more, I think it is a good idea. It is a good idea to explain you what does it mean that we have conjecture, because so far I tell you that we conjecture stuff, but the conjecture is based on perturbative computation, which goes up to 5 loops, or 4 loops in the 5 loops for 5-point function and 4 loops for 6-point functions. Okay. So perturbative data. How do we produce perturbative data? Which we look, and with some intuition, we use to guess this system of TODA equation and boundary condition. Well, let's consider the 5-point case. Okay, I have 5-point case. I make a particular choice for the name of the position of the 5 operators, and this is totally generic because I can reach this configuration by conformal transformation. I have 4 points that lie on the plane, ZZ bar, WW bar, infinity 0, and then I have a 5th point that I cannot put on the plane by conformal transformation, which is 1, 1 plus a contribution outside of the plane. This vector E3 is just in the 3rd direction, and I will label by square root of 1 minus V. It's not so important at this level, but it is a convenient choice. So then, how does it work, our algorithm, to produce the data? First, we always choose 2 edges to send to null direction. For example, setting Z bar to 0 and W bar to infinity. It's clear that since you will recognize I'm writing points on the plane using light cone coordinates. Therefore, when Z bar goes to 0 and W bar goes to infinity, these 2 light blue edges are indeed in null in light cone direction. Secondly, I consider the simple Taylor expansion of these 2 edges of one extreme, that is of the field that lie on one extreme, around the other. Okay? And let me point out that, as you see, I'm considering only the inside part of a tree-level diagram, right? I'm already considering only what I will call then null polygon. Everything which is outside is already factored out. So also the SUN index structure of the fields that appear will be open, okay? So yes, I'm just doing a Taylor expansion, you see. I have a sum in Z to the J and in W to the J prime, 1 over W to the J prime, because I'm expanding around infinity, of what? Of a 3-point, now this is a 3-point object, because this point is 0, these points are in 0, these points are in infinity, there is insertion of some derivatives over certain points, okay, because I'm expanding, of course, and then there is a third point, which is always this third one. Now, at this point, what are the objects sitting in 0 and infinity and in the third point? Well, there are fields. So there will be, here, let me consider, for example, that the thickness of these 2 blue bridges is just 1. Okay? And similarly for the thickness of the other black propagators. But this is really, the thickness of the black propagator can be whatever, bigger than 1. Okay? It's not important in the null limit. So you can easily identify now what are these states in spin chain language. You can identify these points, 0 and infinity, and the third point with spin chain states. Okay? So I have a first field on which I act with a certain number of derivatives due to the Taylor expansion, then the 2 blue fields, and finally the fourth field. Okay? Similarly, in infinity, I have a first black field that connects to 0, then the 2 blue fields, but the second blue field and the last black one are, of course, acted on by derivative due to the Taylor expansion once again, and then I have one emitted and absorbed field, if you want. Okay, so I have 2 fields here, which should contract. Okay, then these states, these bra and cats of a spin chain should contract. Now, these states are open states. They don't have cyclic boundary condition because I am factorizing the sphere into 2 disks. Okay? Right, so now I hope the colors are visible. You see this yellow contracts with yellow, blue contracts with blue, and brown contracts with brown. Okay. Okay. So the open spin chain states where excitations are derivatives. So I can already tell you that, and this is an observation, in fact, is, if you want, not that trivial, that in the computation, in this double scaling limit, it's not important what is the SU4 index of this field. Right? The only thing which matters is that there are scalar fields, and what matters is the number of derivatives acting on them. Okay? So you don't really need to distinguish. Excitations are purely given by derivatives. Okay? And in fact, what are the quantum corrections now to these objects? Well, what would you do when you? It's similar to what you would do in a normal, in a usual OP, right? You put close to each other 2 operators, and you exchange a set of primaries that carry a contribution of the type e to the minus log of z, or log z bar, times the scaling dimension. So similarly here, on the state in 0 will evolve under the action of the dilation operator, which is the one-loop dilation operator, as I explained, which is the only quantum correction part important in the Lightcon double scaling limit. So e to the minus log z bar to g square, one-loop dilation operator, and similarly e to the log w bar g square to d. Okay? Because w bar, which captures the dependence in w bar and z bar once we set these 2 edges to be null. Okay? So the only computation we have to do is to take this bottom state, which is the state at infinity, evolve it in applying the one-loop dilation operator in the exponent, similarly taking the top state with insertion of derivative j prime, which is the state in 0, evolve it with the again one-loop dilation operator, and then contract them among each other and with the state, with this third state, which is more formally written here in the middle, and compute what is the number. So yeah, we really get tables of numbers. when we study different value of changing the values of j and j prime. Okay? This number is what we call stampede, because in a sense is the movement of derivatives which are on a first side here in 0, that they should move on they should run away, in a sense, far away from this first side, because you see in infinity there is no derivative, so if you would have derivative in 0 but not at infinity, this would give you 0 because of simple scalar product rules. So somehow they are running away like in a stampede. Okay, knowing these numbers, knowing this stampede, you can then resum your Taylor expansion of the two null edges and get a function that loop by loop will be a function characterized by certain prefactor as power of log. There is, of course, a stratification in logs, and which multiplies a function of the other cross ratios. Okay? So we have 5-point function, therefore 5 independent cross ratios, z bar, w bar, and this fifth v variable. And this function is what you really obtain out of the resummation. Okay? Now the point is, how do we recognize out of a table of numbers that we can compute with Mathematica what these functions are? Well, we use, and I'm really grateful for this with the previous speakers, we use symbols, because thanks to the fact that the one loop dilation operator effectively acts only in its SL2 component, so it doesn't distinguish different SU4 indices, the result, this function f that appear loop by loop with a certain stratification of logs, are always purely transcendental function. There is no rational part to guess. This is an effect of having SL2 only in this limit. Okay? Otherwise, you would have indeed some non-trivial rational prefactor related to leading singularities of the various Feynman integrals appearing in the perturbative expansion. Okay? So, long story short, you get at every loop order, say g to the 2m plus n, a certain term in log m log n, times a certain function, and you here recognize that the arising of the variables t that I introduced in the beginning. So g squared log, in fact, is, if you notice that log of z bar, log of w bar is distance, is log of the distance on this first edge and this second edge, these are variables of the type log, g squared log of x squared of a certain distance, log of x squared of another distance. So finally, this is how we produce data, the various data for the various possibility, given the various number of bridges, okay, in this pentagon, starting from a very simple iterative application of one loop SL2 dilation operator. Okay? So then we have the data and we work on this and we guess and we check Toda equations. Okay. So let me conclude. What are the next steps of our research now that we believe that we know very well this null limit? Well, it's going to more general kinematics, but still staying in this simplified regime where the sphere factorizes into two disks. That means that we can mix the condition which allows us to cut a closed contour and factorize indeed the sphere into two disks by mixing edges which are null, for example, and edges which are connected by a very large number of propagators. Okay? So mixing the two conditions of large charge used in Franck's octagon and the null distance that we use in this work. In general, we expect then this object to be, of course, richer in terms of kinematics, and to be described still by a certain expansion in leading logs, but to fully capture, and not only leading logs, the dependence on the three other cross ratios. In this sense, it would be also easier, very nice to understand, not easy, absolutely, but very nice to understand what is the relation, as we have a relation between 20 prime and null polygonal Wilson loop, what is the case of this relation, if there is such a relation. When we don't have 20 prime, we have longer operators, so we have non-zero bridges, which is those functions that solve Todd equation. What does it mean in terms of Wilson loop? Is there still a correspondence on the Wilson loop side in that case? There are nice determinants. After all, this Todd equation takes the form of determinant. And the determinant appears also in localization for Wilson loop. So it could be a coincidence, but maybe not. And also, could we derive directly these null polygons, not from our algorithm, but from integrability, from hexagonal formalism computations? And is this result valid as it was suggested to us by Grisha-Korczemski? In general, quantum field theory with 0 one-loop beta function, for example, even in QCD, when you set number of colors and flavors such to make 0, one loop beta function coefficient, and one loop because the dynamic is one loop, as I explained before, for these leading logs. Or even more, we can think about subleading logs, noticing that in the square case, we derived a Todd equation, even for when we include first subleading logs with Pedro, or even for finite number of colors in the theory, as was actually suggested by Thiel. It would be interesting to see if this factorization still goes on. And maybe I should add, for example, a question by myself to Eduardo. What about determinant operator? Okay. So could you think about something, some factorization, even if you have instead of trace, single trace operator, single determinant, one of BPS operators in the theory? Okay. Thank you very much. I hope it's correct, it's Google Translate.
Question? You mentioned that you get these Toda equations in the coming from Toda field theory. Could you imagine some way where you would quantize and you would get, instead of derivative, you would get a finite shift, so similar to Hirota equations for characters and so on?
So we have finite shift, right? But
I mean, in the left-hand side, you have derivative in your parameter.
Yes, in the left-hand side. That's right. The short question is no, because that would mean to discretize this cusp variable. I don't know what it would mean.
So this determinant is very similar to the expression we found with Amit for the two-point function in near BPS. If you like replace it on some angles in the Wilson cusp by your S, I guess you can match it exactly. So is there any reason? And it's also obviously something which Schroter can connect with localization. So is there any reason why it's like that? Can you see any link?
So this is a very good point. Actually, many people always point this out, because also from localization there is really, indeed, as you say, there is right some twist, some angle, but after all, it's a determinant of modified Bessel functions. Well, the origin of this localization result and of our result seems very different, because we reach it in this very particular kinematic. So in fact, we do not know. But due to the correspondence between null polygonal Wilson loop and correlators in this null limit, I think it is a very interesting direction to explore. Maybe not starting directly from the localization point of view.
Following up Cole's comment, I suspect it's related to the following fact. So if you consider very large spin operators, then it's often easier to consider it by mapping it to ADS3 times S1. And once you map it to ADS3 times S1, at weak coupling, you can integrate out KKMOs and then reduce it to the 2D mills with some higher derivative corrections. And in 2D mills, like often you get a really expression similar to that. So I think I suspect like it might be coming from the fact that both localization and this large spin limit or like a null limit are related to the 2D mills.
Hi, very nice talk. I was wondering, is it possible to play a similar game in a three-dimensional theory like ABGM, for which we don't know, I mean, so much yet?
ABGM?
Yeah, can you play a similar game and get
Yes.
maybe some determinant prediction for some correlation function in ABGM?
So, it is definitely possible to play this game. Now, the main difference, it is not in how to produce perturbative data. We can produce perturbative data, assume that our stampede algorithm can be applied in the same way, and in fact we did and already tested on some known cases, for example, the 4-point function of 20 prime. But the problem is on the Ansatz. Okay? So in n equals to 4, we know that at n loops, here we would need an Ansatz that in terms of symbols, I mean, even without symbols, these are uniformly transcendental function of n letters in the symbols of length n. Okay? And these are what? Multiple polylogarithms of Goncharov polylogarithms which have been explained in the previous talks. Now, in ABGM, this is not the case. Functions that you observe appearing are more complicated. Okay? And in fact, now I'm stimulated by this morning talks. Maybe one should look at the basis of elliptic polylogarithms or stuff like that. But even more, there is another point which we couldn't clarify far when we compare our knowledge from the perturbative data spin chain method and spin chain method wise and Feynman diagram wise. Okay? So in n equals to 4, for example, we know that all the functions will enter here will be ladders or determinant of ladders, in fact. In ABGM, you can try to reproduce the same logic and start to compute this analog of 4-point, for example, 4-point conformal integrals, and compute them at least in the Lightcon limit, because we need only their leading log. But in fact, what you would immediately guess it enters is not enough to explain. It's not enough to explain the result that one gets both from the OP and from the perturbative data, which match with themselves. So, yeah, we don't know yet. We don't have our feet on firm ground yet. But I don't see any reason why it shouldn't.
No more questions. So I would like to ask something related to your last transparency. So the last one. So you mentioned total field theory, yes, which appears in the general light-like polygon. Yes.
Yeah.
So maybe this is related to, I mean, if you have just a square, 4 points, then does it mean that you have also total field theory
no.
equation?
In that case, you have the Todd equation due to the fact that 4 points is a simple situation where you have only z and z bar, you have only 2 cross ratio, and therefore in the double scaling limit you have only one variable. Okay, so for 5 points you have 5 variables, t1, t2, yes. t5. For 6 points you have, and so on. But for 4 points you have only one variable. And in that case
but
you have therefore not field theory. You have only time variable, not space variable.
Well, but you have z and z bar. And you can take one variable, which is the logarithm of z divided by z bar, and the second variable, which is the logarithm of z times z bar. So you have two variables, and actually you have a total field theory equation which depends on these two variables.
Yes. It's true. That's true, that's true. This is why I'm referring here to these subleading logs. In this, we also observed this in this work, just for the first subleading logs, that in fact you can, in our work we called LL bar, the S variable, and L over R bar, somehow this correction. And it is it becomes field theory. And in this, following these lines, therefore, we hope and so far believe, but one has just to compute, that maybe our equations that are valid as total field theory for higher polygons, maybe they just remain untouched when we go to subleading logs for higher polygons, and the only difference at that point arises only from an improvement in the boundary conditions that will take into account subleading logs.
I see. Oh, thanks. Okay, thank you, Enrique, for the very nice talk.
Thank you very much.
So we have a 15 minutes break before the last talk of this afternoon. So, the last speaker of our this afternoon is Andrew Lyashik, who will speak about new constructions of Bethe vectors.
Can I speak now? Does someone hear me? Yeah, it works. Yes, it works. Yeah, so hello everyone. I want to say, yes, I'm happy to be here. I appreciate to all organizers for invitation. It's a big honor to me. So I want to talk about some construction of Bethe vector. It was known 15 years, maybe more, but was not realized potential of this construction and how much good physical stuffs can be calculated using this construction. And I want to present this story to you. Maybe someone of you finds something interesting for yourself. So, okay. So we start with usual case, GL2, sorry. We use the most simpler hermetices. We have usual algebraic Bethe Ansatz. We have 2x2 monohermetices, and it satisfies RTT relation. It's usual stuff. And we works in algebraic Bethe Ansatz approach. It means that we suppose existence of some pseudo-vacuum vector with some special properties that lower part of monohermetics annihilate him, A and D act as in diagonal way, and operator B produce new states. It's like creation operator, so it's usual. And when your operator C, A, and D act interval way onto vacuum, you have only one possible way to choose choose constructions. It's just product of BBB onto vacuum with different spectral parameters. So when you have GL2 case, there is not so much freedom to choose, and we start with this, and usually it succeeds. So it was known if you act by transformatics, switch trace of monohermetics onto Bethe vector, and parameters satisfy Bethe vectors, then our Bethe vectors becomes eigenvector for transformatics. So I hope so. It's very known, simple story for everyone. And what if we can change coordinates onto monohermetics? So we make something like Gauss decomposition of monohermetics. So just formally for GL2 cases means that we make a substitution like shown in this formula. Formally, it means that we decompose monohermetics in product of three matrices: upper diagonal, and lower diagonal matrices. And then what happens with we try to look what happens with commutational relation. So RTT relation can be rewritten in terms of this operator in this way. You have these 8 relations, 6 here, and 2 more here. So we can rewrite RTT algebra in these 8 relations. And this some way to, you think about this Gauss decomposition like just change of coordinates onto monohermetices. And just another stories. Yeah, so if you substitute this construction to Bethe vector, usual one, BB, you becomes to this huge formula, which is not so nice. It's worse. It looks worse than previous one. Nevertheless, you still can work with it. But I make the claim that this formula is exactly the previous one when we substitute our Gauss decomposition representation and compute all k to the right to vacuum, annihilate to produce this lambda, and that's it. So this formula not so good to work with it because you can't calculate stuffs. But there is a way to fix this complexity to rewrite in another. So there is some way to simplify this representation to use auxiliary stuffs. So to do it, Yeah, so there is f. Yeah, so f is part of Gauss decomposition, so if you see this story, this b it's f over multiplied by k. So BBB it's product f's k, fk, fk. Then you use this commutation relation this from the second row. You commute all k to the right. You have a lot f's, so you change one k to two f's, and each term grows number of f's. And finally, you have product of 1f, 2f, sum of n minus n f's. So we have some triangular complicity of f's. Yeah. So its functions, its operator. Yeah. So to fix this complicity, we introduce double Youngian. It's very known from a mathematician's construction. Nevertheless, if you try to release it, you can think that you have just two copies of RTT relations that connected with each other. So there are four RTT relations: for plus Mondrian matrices, for minus Mondrian matrices, for plus minus, and minus plus. So it's like RTT, but connected one. And for each Mondrian matrices, you can consider Gauss decomposition, and then you have 8. Yeah, no, it's not the different example. It's the same example. I tried to explain how you can simplify GL2Ks. So how does this construction work on GL2Ks? Because for higher runs, you can explain it on Blackboard. It takes a lot of times. Maybe it's one case when you can understand everything clearly. Maybe also GL11, but not now. Yeah. So you start from RTT with one Mondrian matrix with 4 operators, and now you have 2 Mondrian matrices with 8 operators that called k plus minus 4 and 2e, 2 f's. Is that okay for you? Yeah, okay. No, I think that let's consider GL2 case. We choose 2 GL2, one we called T plus, another we call T minus. They have the same R matrices, and moreover, they connected by some plus minus RTT. So in this sense, it's the same construct. It's the same story. So you can think that T plus it's our start initial Mondrian matrices, and T minus it's some external Mondrian matrices. They somehow connected with this one, but it's a separate one.
But it takes on the same space?
All our constructions works in such way when T minus never act. So for us, it's somehow formal construction, for formal part of story. Yeah, so now we introduce full currents. We define it like difference between F plus and F minus. And let us introduce the most important component of our construction, its projection. Was invented by Horoshkin, nevertheless. So if you have some huge term with F minus, F plus, please try to reorder all F minus to the left or plus to the right using commutation relation like such type. So you see that it's possible, because if you have F minus on the right and F plus on the left, you apply this commutation relation, put F minus to the left, F plus to the right, and it's okay. So, and you repeat it after the end, and you can repeat it also because it's strictly procedure. And at the end, you have some term which normal order in this sense, when all F on the left or F plus on the right. And then projection is some operator, some procedure operator, etc., work in next way. If you have any f minus on the left in your term, then it should be gone to the 0. It should be put to 0. If your term only with f plus, it's still alive. So it's absolutely formal procedure. Yeah. And my statement that this huge formula with many products of f's can be written in compact way using this P plus procedure, P plus projection. So you can see that you have product of f plus minus f minus times f plus minus f minus, and et cetera, et cetera. Then you can expand the brackets, and then reorder in each term. You should reorder operators. Put all f minus to the left, all f plus to the right, and in the end you have some lot of terms which equivalent to this previous formula, this one. So it's absolutely formal procedure, but it have amazing mathematical properties from quantum algebra. Yeah. So you can write, so you can try to understand this procedure. So it's for a moment just formal procedure, but it can be proven that it's the best and very convenient to use it. Yeah, but yeah. Yeah. Yeah, but it's some invert logic because, of course, it was not invented in GL2 case. It was invented in higher runs. But to prove that higher runs, this procedure equivalent to nested Bethe-Ansatz procedure or trace Farchenko formula, it's very hard problem, very hard combinatorial problem. It's done, but it's very hard. And there is no possible way to explain it in few hours. It's really huge works. But I can explain how it's worked for GL2 at least. Yeah, so let me say how it's some points. So this representation called quantum algebra was invented by, it's called new representation of Yang-Yan invented by Drinfeld in '76, maybe something like that. So it's somehow very natural way for mathematicians think about quantum algebras, for RTT relations, but from absolutely opposite side. For centuries, I mean, okay, for last century, mathematicians invent a lot of things about quantum algebra, and usually physicians can't apply it because it's absolutely another language. But this construction allows you to apply mathematical property of quantum algebra to physical stuffs like Bethe vector, etc. And it can be done, and it's done. Yeah. So it was the GL2 case. Okay, so let me explain. Let's say, so for the next, we can consider some RTT relations when our Mondor matrix is n by n matrix. And it can work more or less for wide class of hermetices, even not differential one, with not difference depending on spectral parameters, but wide class actually. And our hermetices for first order should satisfy Yang-Baxter equation. It's condition of consistency of our algebra. Then we ask, then standard story that we can produce transfer matrix which is trace of Mondor matrix, and its commute, and its way how RTT relation produces some integrable system. You pick up this transfer matrix, expand in some area, pick up some coefficient, and call it Hamiltonians. And sometimes it's very nice, sometimes no. Yeah. So as I work in algebraic Bethe-Ansatz, it's crucial point for me to have vacuum vector. And for me, vacuum vector it's a vector with following properties. All lower diagonal elements of Mondor matrix act as 0 on this vacuum, and all diagonal elements act in diagonal way. So this vacuum is eigenvector for all diagonal part, and I can lay by its lower diagonal. Yeah. And then, yeah, at the same time, I don't speak about some representation. It's not field representation. It's not vector representation. It's something like high weight representation for algebra, this one, but without specification. It's finite or infinite or something like that. Yeah, that's my approach. So it's my framework. And so as your all operators except upper trigonal law act in some trivial way onto vacuum, all freedom what you have, it's act by upper trigonal elements onto vacuum and try to construct some Bethe Ansatz Bethe vector. It's done for wide class algebras. Usually it's called nested Bethe Ansatz. It's some construction, very inconvenient to use it, but there is. But I want to propose another construction which equivalent to this one, but with very, very better properties, it seems to me. Yeah. So the crucial idea, it's Gauss decomposition of modern matrices. It was done firstly by Differential in '93. They use trigonometrical version of this story, but it's not a big deal. So you have RTT. You have such type of matrices, Yang-Yang matrices. The most common one for GLN case. You can pick or consider this RTT relation. It's just some components of RTT. Yeah, it's OK. Then you consider Gauss decomposition of this story. So you want that your Mondor matrices, it's product of upper diagonal, and lower diagonal matrices. So it's crucial point. Try to understand me that I read it a few times, but it's a really crucial point. If you can do it, if you can decompose it, and you can rewrite RTT relation from this form to some very familiar from mathematicians that's called second differentialization one, then you more or less succeed. Yeah. Then you can use some standard approaches and you can calculate a lot of physical stuff. Yep. So direct answer was done by Differential isomorphism. That your diagonal part, your k, I, j, they compute. So we call it Cartan part of algebra. Then very natural thing that f, it's part of which call positive Borel. E, it's another part that we call negative Borel, but okay. And they have very the same computational relation as for GL2. So this part, like GL2, so elements near to the diagonal, they act as GL2. And if you're familiar a little bit with representation theory, it's a very natural way to act. And the difference, when we try to compute this E with neighborhood, when GL2 case, you have only one E, one F. So there is no problem. So there is no question to compute E with another E. In our case, answer that E, it's simply one, so it's the closest to the diagonal E. They compute if distance more than 2, so E compute with E plus E I, compute with E I plus 2, and etc. But it's not compute for the closest one. And this is the answer. And we need this formula if you try to, because we need to reorder operators, F minus to the left, F plus to the right, and we need formula of such type. It's not whole algebra. There is much more complicated computation relation, but the most important is this one. In some sense, they define algebra in unique way. The other can be constructed as consistency of this algebra up to some serial relations, but it's some story, don't worry. Yeah, so surprisingly, but formula have absolutely the same form as for GL2 case. But in our case, we have not only one F, but we have n minus 1 F. And if you're familiar with stuff like nested Bethe Ansatz, you know that for GLN case, you have n minus 1 type of beta roots. You say we want R1 type of first one, and up to the last one, and we want Rn minus 1 roots of the last type, and then you put f's of each type with E, with some own spectral parameter, put in put in some product, and then use the same procedure, just projection, f minus to the left, f plus to the right, and then these constructions produce you nested Bethe Ansatz or trace Farchenko approach, the same off-shell Bethe vectors. So this formula is equivalent to nested Bethe Ansatz, to Tarasov-Farchenko constructions. Nevertheless, this simple idea, not idea is complicated, simple representation for answer, but it's produce you the same story. It takes some experience, it requires some experience to work with it, but to show you answer, not so much problem. Yeah, so using this, so there is some question can be here. Can we change order of f's? And more or less, up to some normalization, it's not change anything. So you can put in any order, and it's not affect on your algebra, on your Bethe vector. So only up to some normalization. So there is no much freedom. You put f's in any order, and it works. And me, with my collaborators, to show in some papers how this construction can be used for calculate actions of modern matrix entries onto Bethe vectors, scalar products, some norms, sometimes even determinant forms for on-shell, off-shell Bethe vectors, sometimes no, sometimes determinant representation for form factors of local operators, sometimes no. But if you have such type of formula, you always can do something like off-shell scalar products in terms of partition functions and norms, Tij action onto Bethe vectors, etc. So it's much more than can you do from Tarasov-Farchenko construction or usual nested Bethe Ansatz construction. Yeah. So, yeah, and it was known 15 years ago it was opened by Khoroshkin, Pakulyak, and Rikis. It was very old science. A story about physical stuffs, it was done by me with my collaborators, but nevertheless. And last few years, I spent my time to try to generalize this construction to other series. So we consider this Zamolodchikov hermetices. This is the most common one, so it's for SP, for SO. And we prove that you can use, so before I say the answer, I want to admit a very, very important part of story. So you see, these hermetices have two poles, not one. The second poles have a residue with rank 1. So this Q operator, very tricky one. The square of this operator is n, so it's projector in some sense. So square of Q is nq, sometimes minus nq, but it's details. So square of this operator more or less proportional to themselves. And rank of this operator is 1, and it's transposition of P. And it's, for symplectic case, it's transposition with some signs. Yeah, and existence of this Q for SP, for SO, for orthosymplectic algebra, a lot of examples, always give you some center of algebra. You can think about the center as quantum orthogonal condition. You have orthogonal algebra, it's okay to have something like orthogonality, at least in quantum sense. So it's provide you something like that. And if you try to inspect this algebra for current level, it's very, very nice connections between simple currents. So if you have n by n Mondrian matrices, you have n minus 1 simple currents, and this orthogonality is not up to main diagonal, but the second diagonal. So it's give you some sort of like connection between the first and the last current. So it's, in quantum sense, say you that your monodromy matrices is symmetric up to second diagonal. It's something like this one. It's hard to think about this condition in this way, but if you try to inspect in current level, you see something like that. F equal F prime, which oppositive current from another side, up to some shifting. And this shifting is its quantum part of story. It's calculation. It can be proved, but it's calculation. Yeah, so in this sense, you start from n-1 independent simple current, but quantum orthogonality condition, this one, restrict the number of independent full currents in 2 times. So more or less, it's n over 2 independent full currents. And in this story, at the end, one can prove, we do it, we did it, answer that Bethe vector is product of independent simple currents with corresponding spectrum parameter, and the same way as previously. So now we have received, in this case, you make Gauss decomposition, pick up simple currents, make double Young-Yan, construct full currents, write a product of them, reorder such all F minus gone to the left, all F plus to the right. Then you apply projection, and then you apply this huge formula to the vacuum, and it's produce you Bethe vector. And its formula looks like previous one. And it's very, very amazing part of story. So more or less, answer is the same for whole algebras, A, B, C, D type. And there is paper of Resurgence and for Martins, I don't remember with him, maybe with Ramos, but I'm not sure. And they have something like nested procedure for other series. And I try to compare this construction for small ranks, as they coincide. But I don't try to even compare it for higher rank because it's very, very hard to work nested Bethe Ansatz for other series. Yes, I don't like it. Yeah, but my formula, amazing. Work the same as for GLN case. It's give you scalar products, norms, action of Tij onto vector, etc., etc. So if you can calculate something for GLN using my approach, you can also calculate it for Bn, for Cn, Dn. Actually, it's applied for much more wide class of models with natural symmetry, like algebra symmetry or something like that. But we restrict ourselves for the moment. Yeah. So for this conference, I tried to, it was my whole idea to apply this approach for Hubbard model. Yeah, it was actually a challenge problem. And we should to start from something. So we start with Bézard hermetices. It's not usual form, but you will see. So one can separate Bézard model in three terms of different type. First, so it's some notation, usual one. If you're familiar with Bézard paper, with Bézard hermetices, it's the same one. But I prefer another choice of grading because if original way they haven't good Gauss decomposition only in this way, only with this. You should have symmetry between term position by second diagonal. So yeah, in Bézard was 1 and 2 was this grading 0, and 3 and 2 was and 4 was this grading 1. So it's a little bit another grading. In the rest story, it's more or less the same. Unity is slash operator. So you see that it's like diagonal, but with some functions. Here you have something terrible actually. But in some sense, if you consider residue u equal v and put v to the infinity, it's unity. So it's proto-unity, you can think about it. P looks like the same. So up to some numerator which never, yeah. Yeah, so I say, if you start with, yeah, it's first term of my representation of Bethe hermetices. Yeah. So I just tried to think about Bethe hermetices as one more orthogonal like hermetices, but with some stuffs. Yeah. And its P part, it has residue at point u equal 1, and residue is exactly super permutation. So it's, yeah. And Q, it's such type of operator. It has a residue in special procedure. So you should put, they called it procedure like conjecture, yeah, no, conjugation. You put x plus minus of u and x plus of u to 1 over, and then you have pole at this point. Yeah. So it's such type operator. So you can think about this in this way. So 1, if you put u equal v, put v to infinity, you become unity. P, it's operator which have residue with super permutation and something more. And Q, it's operator which have pole equal to some Q, similar to previous one, with gradient, with super story, but only after this conjugation of one of parameter. So it's such type operator. Yeah, so it's such type. And you have this very standard story for super case. If you have something like gel nn, your q square, it's not proportional to q, but equal to 0. It's the same for OSP nn and for some other type of algebra, but it's okay. It's in some sense, if you can say about superalgebra rank, it has rank 0. And it's skew transposition with some signs of P. I will explain it a little bit later, but nevertheless. Yeah, so you can think about this Shastri, no, Bethe representation of hermetices in this schematical way, that it's 1 plus P over U minus V plus Q1 with some, yeah. So I tried to say that this hermetices very close to orthogonal hermetices. Yeah. So if you have this representation, first your intention is try to understand what is the center of the algebra. And I don't know why. I didn't find it by the paper. They have another center, which some function of this one, but there is one more center of such type. Maybe I miss, but I did not find this center in Bethe paper. Nevertheless, there is paper, there is center, which suppose that there is some constraints on your coordinates onto Mundum matrices, like in orthogonal situation. Yeah, so transposition has this form. It's standard super transposition for any GLN, but this special part of this gradings, which only about Hubbard, there is no such sign for orthosymplectic algebras. Yeah, so it's some special part, but nevertheless. Yeah, so as I say, the center give you some constraints onto currents, simple currents. So current E34 connected with current E12. Yeah. And there is some connection between Cartan part of, yeah. So more or less, it's with some special points, but it's usual story for orthogonal algebras. Yeah. Then I try to finish Gauss decomposition of this algebra. Yeah, and I succeed. Yeah, you can surprise, but it's done. And if you see for E23, K2, K3, you have absolutely SU2 algebra, absolutely one-to-one, as was shown on the first part of my talk. So you have algebra, and in a part, it's absolutely SU2 with any points, absolutely, yeah. And part with E12 and K1, K2, it looks like fermionic, but with some special stories. It's very fermionic, but not exactly. Yeah, sorry. Yeah, in this sense, it looks like actually, when I finish with it, it seems to me this algebra very, very similar to GL21, but with some special story about E, with this fermionic part. Yeah, so it's okay when E part and F, they dual, so they have the same computational relation up to some details. Then if you try commute E with F, so F with E commute as in GL2 case, they anti-commute as for GL11 case, but functions a little bit not usual, but very close. And then if you try to compute F with E, so it's fermionic, so the okay, it's exactly the same as for GL11. It's the same story. It's exactly the same story for GL22. But the problems begins when you try to compute E1 with E2, E12 with E23. They have so the main part, this one, we called it's the crucial part. These parts have influence on the Bethe equation actually. So it's the most important part. We call it full current. It's full current, and we usually call it local terms because if you see precisely, all these terms have the same spectral parameter. In this point, you have different one, but the same. In some sense, it's important part, crucial part, and the rest, it's some remaining, which usually not important. But in this case, somehow it's turned out that this algebra looks like GL21 when your fermion part live onto two-sheet covering of complex plane. It seems to me it was known any type of such algebra. No one. I asked some special guys, they know, and they say it's something strange, something pure. So if you want, truly symmetric of this Bézard hermeticis, it's GL21, or you can call it SU22, central maximum extended if you want. But this is the main point. It looks like GL21, where fermionics live on two-sheet covering of complex plane. Yeah, so it's important part of story. If you mathematics, you like it, you can try to invest in this algebra to try to calculate stuffs, but with physics, usually. And I tried to apply this construction for Bethe vector, and actually I succeed. So I prove that Bethe vector, in this case, also looks the same as previous one. You put full current for F plus, F minus. Put all F minus to left part using this formula. So these coefficients arise, it will arise in coefficients of terms. So it's not so simple, but after all calculation, you have simple rational part and simple, not simple, but this part. But after the end, you have some formula. For in this projection. Because the third is connected to this first one. as I say, you pick up only independent currents. And third current is connected to the first one. It's the same story for orthogonal algebra. You have an independent current. You drop all dependent current, and the rest have their own spectral parameters, type of parameters. For GLN, for GLN, you have n-1 type of currents, n-n beta roots type of them. For SO2n, you have only n independent current, n independent beta equations. And in this sense, as this algebra is algebra of rank 2, not 3, 2. Because you have center which restricts one parameter. After all, your algebra is algebra of rank 2 with 2 types of currents. You have only 2 types of beta roots. Sorry? It's a good question. And in some sense, it's of course depend on sheet of choose of sheet. Yeah, it can be. Yeah, It's in some sense it's hidden, but so then you can try to calculate action of Mondrian matrices. Trace of Mondrian matrices that called transfer matrices onto this beta vector, and then you become to the formula for eigenvalue of transfer matrix. It's up to some very, very non-trivial factor. It's very, very nice formula for eigenvalue of Mondrian matrix, of transfer matrix. As usual story, you can, from your point of view, you can consider residue of this eigenvalue, and you obtain something like beta equations. I obtain it directly from action of Tij, nevertheless. But finally, I become to this nice, very nice GL21 beta equations. And it's correct answer because it was known from Ansatz by Shastri. It was very, very known before. But the most nice part of story that in some sense, it should be something like special modification of GL21. Because beta equations, etc., algebra looks like GL21, the rest stuff looks like GL21. So it seems to me that I'm finished. Yeah. So I want to say that if you want idea to understand from my old talk, that if your beta vector somehow connected this algebraic structure, like Yang-Jan, quantum affine algebra, because this structure work for a lot class, I mean for very, very wide class of models, supersymmetric, not always differential type. I have another examples for trigonometrical, for rational, but always you make Gauss decomposition, but you need algebraic beta Ansatz approach. Lower diagonal act is 0, diagonal act in diagonal way, upper diagonal is some creation operator. Then you make Gauss decomposition, pick up independent simple currents, build full currents, make projection construction, apply to some vacuum, and then it will be beta vector, even in Hubbard case model. So Hubbard model case, yeah. Lefin? Sorry, yeah. So, I'm finished.
Thank you, Leszek. It's not very clear. You said your gradient is different from the aromatics of Bethe. But for example, in SL21 case, we know that when we change gradient, we get different beta equation, yes? So it's not very clear.
No. So in this sense, Bethe have something like GL21, but I have GL12.
Ah, okay.
Yeah, but it's a good point. So if you consider vector representation, so I mean fundamental model, there is no big difference. If you consider the whole representation model with non-trivial lambdas, all of them, maybe there is difference, but it's very special question.
I just about right.
Yeah, so I need this change of, so it's not important for Bethe because it's just relabeling of strings and rows and columns. I change the second and fourth columns and rows. So for Bethe, there is no problem. But it's a problem for me because I need that my Mondrian matrices should be skew transpose up to second diagonal. So I need this one, and it's not important for Bethe.
Okay, and the one more question, you said like your method is applied for Y class of model, but somehow in your formula I saw somehow k minus 1 appears, so Cartan are inverted somehow. So does it mean that it will be not applicable if Cartan degenerate, if it's can?
Yeah, so if Cartan is degenerates, we have a problem. Because you can calculate even Gauss decomposition actually, because it's something like divide to 0. Yeah, so maybe there is another way to think about of this special type of models, but I don't know at the moment. Yeah. Yeah.
So your currents K for Hubbard. So I don't know if you wrote it down, but they also commute for the case of Hubbard?
Sorry?
Ki, they commute for Hubbard.
Yeah, all Ki commute with each other.
Okay, can you diagonalize them?
Sorry?
Can you diagonalize them for Hubbard?
Diagonalize in which sense? In terms of what? I need some representation for this.
Yeah, okay, so for defining representation. Defining representation, for example.
I didn't try, but I believe, of course, I can.
Okay.
Yeah, because, so, all my story that you shouldn't care about finite representation if you, so it works only for highest type, so of representation with highest weight type. Yeah, so it's algebraic Bethe Ansatz approach. In this case, you shouldn't care about the lowest vector, because it's something like model in mathematical science. You just free action of upper triangle, and then you try to understand, to find some correct Bethe vector for each shell. And in this sense, I know the answer. You can pick up some special twist, and so I should think about this idea, but I believe that you can do it choosing some twist.
Yes, so the reason I ask is because for Hubbard, this twist does not exist.
Yeah, because in Hubbard there is a restriction. This twist should be
Determinant 1 is this, yes.
Yeah, so there is some restrictions for this one. Yeah, so you know better than me. Yeah.
So, okay, well, so you haven't yet tried to diagonalize K. Well, in that case,
I haven't tried.
Okay, so we'll talk later then. Okay.
Yeah, we can talk about it. Yeah.
So answer to your question. So Beiser-Studacher-Bethe equations only work in beauty grading. So Bethe equations for this model only work in beauty grading. Trying to do any other grading of the Dynkin diagram will produce horrible equations. So this only unique choice of gradient, which actually was chosen today as well for our matrix. Choice of gradient for our matrix, I mean, you can still get a different gradient for Bethe equations if you just do it cleverly. But this equations actually, this is GL2/1 rational spin chains. So
yeah, GL2-1, exactly one.
No, it's not just 2-1, but it's a rational spin chain. Where is Zhukovsky?
Sorry?
Where is Zhukovsky? I'm confused.
There is no Zhukovsky.
Sorry?
No, so this paper, very old one, maybe Shastri, maybe no. They prove that Bethe Ansatz, in this case, it looks like this one. So it's not new, it's very. Yeah, it was done by coordinate Bethe Ansatz. They proved that, so it's a very old story that we have very, very terrible hermetices with non-trivial functions, but at the end, Bethe equations have difference form. I can show you if you want.
Guys, do I miss something? Where's Zhukovsky?
For Bethe equations, there is no Zhukovsky.
I mean, that is not what we call Hubbard in
Sorry?
this room. I mean, these equations we do not call Hubbard-Bethe equation in this room, but I
believe this equation is exactly equation of Hubbard model. I mean, spin chain called Hubbard model. I mean, that Hubbard model, which true Hubbard model.
Oh, okay, like the honest Hubbard model. Okay. So the actual question I have: what is your formula for twisted affine case?
Sorry?
For twisted affine case.
Yeah.
Your magic formula for B.
Exactly the same as for orthogonal case.
But there should some change, right?
You have another hermeticis, so your Gauss decomposition produce you a little bit different commutation relation on E and Fs. But from point of view of formula, you pick up only simple currents, construct full currents, put under projection, and this works. It's work for other series, for twisted, for trigonometrical. It's always one.
So just okay. So you have the same formula. F's are different, but also Bethe equations are different, right?
There are a lot of difference because commutation relation between F's different for each algebra. I mean, commutation relation between of such type between E and E it's different. So I mean, even this function can be changed, and it's part of Bethe equations. So exactly this function. It's more or less this part of Bethe equations.
Mm-hmm. Okay, so this magic formula is the same looking, but it have but formula is the same looking, right? This is
for Bethe vector,
yes.
In terms of projection, yes, that's amazing part of story. Okay. Miracle actually.
So does this formulation help to compute the scalar products?
So I finished it in last week, so I don't know, but I believe I can.
But for GLN, for example,
it does for GLN, for other series. I believe it can be done, but I don't want to promise that I can do. But I believe it can be done, and I can produce you something like off-shell Bethe vector scalar product in terms of partition function, like Kershtin formula, if you know. And its formula, more or less, always can give you norms of Bethe vector, at least. Sometimes it can give you overlaps in determinant form for on-shell off-shell Bethe vectors, but I'm not sure. But I still don't know, is it GLN 2.1 or it's something another one, because it's hard to understand, but it looks like very close to GLN 2.1.
Well, it seems that there are no more questions, no? So let's thank again Andrei.
About the poster session. So we can start in like 10 minutes maybe on the first floor. If you are going to present the poster, then please check whether your poster is already there.